procedural assemblies, V2.0. We had V1.0 with Alejandra, and Marvin has taken on the second version of this. This webinar, which is going to deal mostly with discrete assemblies using primarily Grasshopper and the Wasp plugin. And if you don't know what discrete assemblies are, you know, you can kind of tell by the images. It's kind of modular systems in very smart ways put together, which you know, Marvin and his team are kind of really excelling at in the real world construction. So that's pretty exciting, exciting stuff. So introducing Marvin. Marvin is an architect, entrepreneur, and founding partner of studio Urban Beta and architecture office Bratke. Marvin works on participatory methods to create inclusive and transformative spaces through predictive planning. He collaboratively works on new ways of social inclusion, both virtual and physical. His research project, Betahood, became a model to promote the start of the new European Bauhaus. He is actively teaching and consulting at various universities like TU Graz, UCL Bartlett, and the AA Visiting School Program. University of Innsbruck, TU Delft, and I don't know how to pronounce it. This one is always difficult for me. How do you pronounce this one?
Always the French.
Yeah, how do you pronounce this one? I don't know.
It's okay. I'm also not good at it.
Yeah. I could say it like very American. He held visiting professorships at Muftius Academy in Arts in Kiel and Universidad Internacional SEK in Quito. His work is widely published and exhibited i.e., for example, the Architecture Biennale Venice, Experimental Architecture Biennale Prague, Munich Design Week, or Forward Festival. So without further ado, I'm going to hand it over to you, Marvin. I'll be here if anything is needed or to be helped. I would like to remind the attendees to please ask your questions with the Q&A button. So there's a button in your bar there that Zoom gives you, options bar. There's Q&A. Ask questions there, or we might miss them in the chat. Yeah, so hand it over to you. I'll be here.
Cool. Yeah, thanks for the invitation, first of all. It's a really pleasure to be here. Also, being at the Computational Design Next last time was really cool organized events. So it's always a pleasure to come back. What we'll be doing, Mike already said it, we will look at assembly structures, we will look at modular building structures. And since this is the second part in the series, it will like kind of like the definitions and the exercises we do will have some stuff in common, but it will also go more into an architectural scale. And there will be 7 exercises, and between every exercise, I would say we make like a 5-minute break, for example. And in the beginning, I just have a little intro presentation, and it's also like an intro for every exercise. In the beginning, there's just some slides introducing our office and just some stuff that we did in academia, and like also how we use these techniques in practice. And how we bring them to reality, that also kind of like there's like a certain tangibility in what we're doing here, and that you guys can have some little insights. And for that, I actually would share my screen. So 1 second. Here we are. I'm not going to full screen mode today. I will just leave it like this. But that's a little intro presentation, so it will also give you an overview what we will be doing and why we are doing it, and also give you an introduction to each of the exercises and put them into context. You heard already in a nice introduction. Thank you for that again. My company is called Urban Beta, And we're working actually where shifts are happening, yeah, where environmental, technological, and societal shifts are happening. And we see there like is a place where spatial innovation can happen in architecture, in project development, and also in research and foresights, which are the 3 fields that our studio tackles. Yeah, Beta is spatial innovation agency. It's not a classical architecture office, and we deal a lot like with consultancy on future trends, but also with developing spatial systems that are adaptive and less statics, and create flexible rooms that can grow with their users. And for that, we do not only work on the architectural part, but also on the business model around it. Yeah, we very much work on circular economy models, and all of that starts with the simplest or with the smallest connection, and then goes all the way up through like the construction process, but also in the business model process, which then enables something that we call space on demand or building as a service. So opening up the construction industry for more service-based models in the future, something we know from other areas as well, like bike sharing or something like that. And we think it is possible with modular spatial systems to arrange also spaces that can grow with us and can be flexible around us. There are like 4 basic values, or purposes we have in the company. It's impact through empathy, which means basically every project is based around a social core, foresight by design, tackling the innovation part of each project, space on demand. I just explained, creating new service-based models in architecture and in building. And then, of course, the circular realization with like really a strong focus on material innovation, on sustainability, and especially on circular economy methods. We have 2 offices in Germany, and Paul of us is also sitting in New York. We have quite an international project range. It's like on this little map, you see like we all worked all over the world and have there quite some experience. And just coming to the webinar right now, it's like I just wrote a question here. It's why component-based design. So just giving you a little intro, starting at the very beginning, or with the digital revolution. It's just like comparison picture of the first computer and of a quantum computer where we are right now. So we see kind of this rise in computing power, of course, the evolution of software as well, of CAD software, of BIM software, and like the possibilities we can do with it. And there have been certain pioneers in the profession, of course, that also brought architecture forward, introduced a new way in computer-aided design. Like you see the embryo house from Greg Lynn, or the Möbius house from UN Studio, that's kind of negotiate like new spatial concepts that are very much based on the evolution of software. And then also kind of bringing like the digital trend, or like this new software movement, like from the late 90s, 2000s, then into reality. This often happens with like a post-rationalization of buildings. On the right side, you see Zaha Hadid building, like very complex curvature and form that is then like facades are panelized, they're rationalized, they're optimized to kind of realize what the computer has given. That's also a point we are today, combined with like new techniques of producing, like large-scale 3D printing, for example, new sandwich components, building components, new materials that all come together, and therefore kind of form something or where we can see, for example, a certain gap. And this is also where our office is like based in, because also when we look at our cities, we think that it's quite yeah, a rigid construct. And we're working on something that's more the diagram on the right side, yeah, from creating like this very object-oriented environments towards something that's more dynamic and human-centered, and is like also can behave with us and around us, yeah, and can react to different flows, to different people flows in the ever-changing environment that is accelerated in the in the internet age, yeah, in the information, in the accelerated information exchange age. And we are working on therefore on open systems. So basically it's kind of a different approach than, for example, the buildings you've seen before with the post-rationalization, because it doesn't start with the big form, but rather with the building block itself. Like I kind of like this comparison photo, like on the left side, there's like an Apple MacBook, on the right side, there's an open source computer, the framework laptop, yeah, even though they look the same, the build up is completely different. Yeah, the one on the right side is based on building blocks, and it's like easy to repair, easy to exchange and extend the computer while keeping also certain looks. And in the building industry, we're also facing these paradigms that yeah, our construction is like basically hasn't changed too much in the last 50 to 100 years. Let's say we still build in a similar way than, like, for example, here, like the Seagram building, yeah, that was built in the 50s. There are counter models towards it, yeah. For example, here, like the Architecture Machine Group, which is the predecessor of the MIT mediated matter group, of course, yeah, that, like, for example, you see like a real-time urbanism where the city actually, it's a city for mice, yeah, but where the city can react to these different streams in real time around in this test case here. And there we come also to some challenges that we're facing in architecture and in construction, namely that today, like, every building is like unique and a prototype in itself. So there's not much repetition today in the way we build our buildings. Yeah, there's a certain limitation in reach and regulations, and there's also, like, in production, maybe like something called a skyscraper problem. So to build kind of a building of a certain size, you need a machine that is bigger in that size. And yeah, in other branches today, you can also see that there are advancements where architects could learn quite a lot. On the left side is the A380 factory. Basically, the whole factory is a giant robot that builds an airplane around it. And this is only feasible because the airplane is a mass product, which would not work with a building, for example, when every building all the time is unique. On the right side, everybody knows that picture of an Amazon center, like a decentralized warehouse with these Kiva robots, yeah, that basically are also like a city in itself that always rearranges in real time. And there are, like, this ideology and this concept you could already see kind of like in the 50s. Yeah, on the left side, it's an illustration from a military magazine, actually, where the inventory and the warehouse itself is kind of depicted in the same way, yeah, like these orange cubes, indicating already that basically they are treated the same. So the building itself can be exchanged with the inventory, can grow, yeah, can change over time. And concepts, of course, that are also inherited with this flexibility. On the right side, Mobi Market in Shanghai, I think. A test project of a mobile supermarket that actually comes to you with an app. And all of these concepts are negotiating like with distributed networks. Yeah, that's what they all have in common. They're not like centralized models, yeah, but kind of what you see on the right side, yeah, that's from network theory from Paul Baran in the 60s. That they are all like node-based systems and therefore have also a certain self-healing functionality in it. And this is also something that we're interested in architecture or architectural systems that we are dealing with. Yeah, we're dealing with self-assembly, or used to deal with self-assembly structures, yeah, of new ways to negotiate building blocks with each other, and this with sustainable material. And therefore, we come to a point that we call like agency in construction. So we think that our building blocks, or to overcome the challenges we had in the beginning, we can introduce building blocks that have a certain agency and independence, and that allow for like reconfiguration, yeah, and therefore also creating like a bottom-up model for building. In the end of the day, where kind of buildings become more flexible, but also more serialized. And kind of this mirrors maybe in this graphic, yeah, like on the left side, there's the suburban model, yeah, very defined through the rise of the car and the rise of suburbia, like a residential model that takes a lot of space, horizontal space. Yeah, you have a garden, you have the house, and today we live in a time of densification of cities. Yeah, more and more people will move to the cities. Like 70% of the people in the future will live in cities actually, and we will have a space program in this. And like spatial systems like this, yeah, that can be reconfigured in 3D space, could be actually a counter model to, yeah, the diagram you see on the right side. And this is also something that we will introduce in the workshop, yeah, with aggregation-based design. That could also, like in our office, introduce like circular economy models out of that, and that introduce also architectures, yeah, that at one day can have a certain function, yeah, and tomorrow or next month they could be reconfigured to something else using the same parts, just in another configuration. And I just put down some software requirements you need for the workshop. I think this was all in the introduction. We will mainly use Rhino, Grasshopper, and therefore mostly the Wasp plugin. There is one exercise. There's one exercise that uses Kangaroo 2, I think. This we will do. Yeah, we will have some form finding in Kangaroo. And funicular surfaces, and then populate them. And in the very first exercise, there's also, I think, some components of the Lunchbox plugin, but it's also not connected to the overall aggregation. So if you don't have it installed right now, that's also not too bad. And then I just wanted to show you some component-based design that we did with students in the past and that we are doing in the practice at the moment. So there's also like a certain connection between academic research and bringing also this research into reality in the end of the day. And like our office is also working a lot at the intersection between mobility and architecture, and we try to bring that back to universities and to our teaching. And for example, this was a project which was about urban automation. It was called the Carrier, and basically it's kind of an architecture system and a drone in itself. So basically like a mobile logistics center that can rearrange over time and therefore become like a carrier pigeon of the 21st century, but can build like this mobile logistics center all around this town. A very similar concept also from the same workshop actually at the AA. The Firefly Space Navigator, and this was also about the question how urban lighting could be more active, could be only used where it's or could be only applied where it's actually in use, yeah, and could travel over the city to also form different aggregations and also architectures for like, for example, festivals or temporary structures. And then could be deployed and reemployed in different locations. And then 1 year later, I think this was last year, we also applied this concept in different contexts. We like had we did a project with the students called Urban Mixtape, where we recontextualize certain elements out of New York, which has also this circular economy aspect in it. There were projects that were about like healing from waste materials, for example, that were reconfiguring like certain elements here in the brownstone houses, the fire staircases, and creating new infrastructure and architecture elements out of it. Here's a little spelling error. And as you see, so you could actually use different parts. We will also do an exercise like this, similar to this in the workshop, where we kind of have a scenario actually where we can build something from waste, where we can build something from used material, and therefore also introduce this circular economy topic, or this reuse topic. And this is just some examples from the workshop that we used to do last year with the students, and some outcomes of it. I think this was 1 year before, also similar topic, also aggregation-based design. This was more on urban scale, creating kind of new community spaces, on top of existing structures in New York, on top of infrastructure, architecture in New York, and also using kind of like these very iconic elements. In this case, like it was like the steel construction from the subway and the train tracks, to reconfigure them and try also in an artistic way, try to create like spatial aggregations from it. Like even towers, like from the billboards, and technical elements from Times Square, completely reconfigured to new cities. And also in a different context that we will touch in the workshop now. We're also dealing a lot with timber structures. So we introduced that at the Bartlett as well, in a studio that was all about the new European Bauhaus, and thinking about how to create like a new aesthetic for the Green New Deal. And this is what the students came up with, like with simple structures that can be reconfigured, that are also part of like the democratization of buildings, where people could are invited in participatory processes to self-build and self-configure the spaces around them. And this also led to like more extreme vertical structures, high rises. And this brings us actually to like this connection between between our research and our practice. This is our most recent project that we just realized, and we also will build again in a reconfigured configuration. This is the beta port. It's a sustainable mobility hub with an on-demand business model, which I was introducing in the beginning. So the whole port is built up from locally sourced components. It's all based on these voxel structures, which you see on the left, like a three-dimensional pixel that can be easily fitted out. That has reversible material connections. And it is completely designed with a design to disassembly methodology in the end of the day. And what you can build from this is modular building blocks that can be reconfigured over time, and you create you're able to create adaptive systems, buildings that can actually last shorter and longer at the same time. And I mean like shorter in the sense that they can change their function over time with their users, and they last longer in sense of building materials, using material passports, or introducing material passports and databases, where like the whole building becomes something like a material depot, but that is not static but flexible in its use. And the whole system is actually or like this is where we're working on right now, the scalability of the system. Right now we are here. Here you see this, it's actually built from certain discrete elements. We have these crosses that we realized, and where you can see the voxel structure. So this is the beta port 1, which was first time realized at Green Tech Festival in Berlin. Here you can see like also the structures. At the moment it's a patented system already. We patented the knot, and it's like an open, it's very inspired by open source architecture. Basically, it's an open system, like with the integration of the MEP like through the timber elements and the charging infrastructure, but not as a plug-and-play system, but as an open system where you can easily exchange the cables and structures inside of the structure with reversible openings in the beams and columns and leading through the knots. And also with that, we introduced for this like a construction process with a quality process as well, where we built kind of like these knots and these boxes in controlled environment, can check them at 1-to-1 at building scale before they get delivered. And this is all about like having a very easy assembly on site, on creating this participatory process of inviting non-professionals and community helpers to build their own architecture. Every part is designed that it can be handled or can be carried by 2 persons. It's all based on like these plug and play connections. There's no prior groundwork needed, and the whole system is also non-invasive, based on these reversible timber joints. So this is the first time we built it, just some impressions, like beautiful pictures that Studio Naro did from it. And also what we introduced the first time with it is an interactive configurator. And also this is something where this webinar now intersects with it. Yeah, we will not build a complete configurator, but like the ideology of component-based design, of course, this is very much inherited in this system here as well. And in the end of the day, we're working on the automation chain, yeah, to create file-to-factory processes out of the configurator, which include the material sourcing, construction, and then, of course, the delivery on site, which then leads to this building system that is ready to scale. And so much for prior work and just introduction to the topic. And now we also want to start with the first exercise. And basically this exercise will give you a general introduction to component modeling. I prepared, it's quite a, I think, like it's quite a variety in this file. I prepared for you guys just like 5 examples how you can use Wasp and how you can use the software, and we will just like after this little introduction dive into it. So we will start from simple component that are scalable. I will just give you like a very short introduction of polyhedra, yeah, of platonic solids, yeah, that can be stacked and stapled in many directions. And these are just some of the building blocks that you will find in the file that can be then assembled in different ways and stacked in different ways. And what we will do is like we will model something as an introduction like this, and then I will show you how you can come from like basic components like this to more elaborated constructions like this, all using Wasp. And this is also where we would switch now. Or where I would switch now from the presentation to Rhino. And and I would say we just start, and I give you a little overview of the file. Basically, here in the front, you will find different inspiration for components, which can all be used as building blocks. Yeah, there's a simple cube, octahedron, then a truncated octahedron, yeah, prisms, pyramids, all kinds of stuff, yeah, that can be stacked and stable. Connectors, we will come to this one in a later exercise as well. And then on top of here, you can see how different components are used. And each of these components has, or basically each of these aggregations has one attributed exercise in Grasshopper with it. Yeah, so we have here the cube, we have here the poly, then we have here the weave, and we have the lattice, and in the end the prism. So this is what you will find in the file. But just to get a grip in the end of the day, maybe one introduction in the beginning. If you don't want to create like these base geometries on your own, then here, what I have here on the right side could be interesting for you. This is basically, and this is at the 0, 0, 0 location. So basically, this is just the generated polyhedra from Lunchbox, yeah. And if you want to find them, then you can just open Lunchbox or type in platonic octaeder, platonic tetrahedron, and then you will find these ones here, right? In this case, it's the octahedron, yeah, but I also already prepared some other stuff. So when you flip this, you will have the dodecahedron, yeah, the tetrahedron. You can just exchange this. And just here with this little grep, I put out the edges and the center points of each surface. But this is something that we will take a look into now as well. And for now, I will just open a new, a new document. Yeah, and we basically will start creating our own geometry. Yeah? For once. And basically, no, what I wanted to do with you, actually, I wanted to go through one or two of these aggregations. Maybe we can also do all 5 of them, but there will be a lot of other exercises coming as well. And just to be not too repetitive, in general, this file is actually rather for showing you only the basics. And yeah, and I would say I will just jump right in now, because I would like to do the very basics with you. I will grab the octaeder here, and also for modeling, I will switch my screen off, just that you have a faster connection. So here, and also what I heard is that we just introduced bifocal, so everybody can see every Grasshopper definitions. So for now, I just picked this octahedron, just zooming in on it. Now, of course, I wanted to give you a quick introduction to Wasp and to component-based design in Wasp. So let's take a look in here. You will find different tabs inside of Wasp. You will have the element tab. So basically this will, this is very important, yeah, because we will create our different elements from here, like from our solids. Then we will create certain parts that have certain attributes from it, yeah, names, which can then be inputted in the aggregation, and then we will use here the later ones to output them out of the aggregation. But you will see how that works as well. We have different rules, which means this is all about how to connect or how the components connect with each other. We have constraints. We will introduce in the later part of the tutorial. We have fields. This is also when you want to aggregate along a curve, for example, when you want to aggregate a volume with components. This is also something we will do later. Then this is basically the main part. This is the aggregation itself. And just to get started, we put our geometry here once, then we do a point which gets the centers of the surfaces we want to connect, and we always need a curve as well. And when you look at this, I prepared these objects already. When you look at this, I always prepared like a center and a curve that indicates actually your planes on the surface, and that will indicate kind of like how your aggregations will work in the end. So let me just move this one over a little bit. What we need now is a connection from direction. Yeah, you will see this here. It's the very first element, which basically introduces your geometry, then the center points on your faces, and then also the curves that indicate always a direction. And what we will do now, I will go here to wireframe. Yeah, we will input the geometry, set one geometry, then we will input the points. But what's very important is to see the points in which order we inputted them. So let me just make a point list, and now we input multiple points. Yeah, let's say here the first one, second one, whoops, third one, fourth one. Press enter. Can you see here with the point list we can see in which direction or in which order we inputted them, and then the curves themselves, they also have to be inputted in the same order. Yeah, so we put here set multiple curves. We go to 0, 1, 2, and 3. Press enter. You will see that then the planes are generated on the surfaces. Yeah, so I will put the preview off, and now we generate a part in Wasp. For that we go to parts, yeah, tab number 2, and take a basic parts. We will not talk about the advanced parts, and what it wants from us is a name. We will give it a name. It wants the geometry, which we can already input. Yeah, this is the base geometry, and it wants to have the connections, and the connections we just defined with our connection component. So we will input this, and then we make a panel and give it a name. Yeah, we could call it Octa in this case, for example. So let's give it a name, and then you will also see that it now functions. Basically, I always group my stuff then, because this is basically how you generate your part. And to get an aggregation from your part, we can go to the aggregation field, take the stochastic aggregation. Yeah, this is like an unidirectional aggregation, and also not field driven. So basically your elements will directly aggregate on top of your first element that you have here. So, and what it wants from us, or what are the most important inputs, we have the part input, yeah, and the part we created already, so we can put this one already in. It wants a number of the aggregations, yeah, and I put in 100 in this one. So this will be your aggregated parts. Yeah, maybe don't put it too high in the beginning, because this could be very intensive in computational power. And it wants some rules. It wants a reset button. Yeah, for that we can do like here. No, sorry. We make a button. Sorry. So that we can also reset this toggle we will need later. And now the most important thing it wants from us are rules. Yeah? So we have to create rules. Basically, rules are which of the faces. Yeah, for example, here when you see, and I want to have a 0 connected to 1, I have to create a rule. And there are different ways of creating rules, and we will tackle quite a couple of them. And I will, the first possibility, quite a simple possibility, is just the rule component. And the rule component wants basically P1 and C1, which is P1, the name of your part, and C1, the ID of your connection. And the name of your part in this case is our Octa. And then for C1, we just create a number slider, like we have 3. We have 3 faces that we 4 faces that we inputted, of course, with 0. And then we connect the rule here. Yeah, we connect Octa again, which means now when I put part number 2 here, oops. So this rule means now that the octa element will connect to itself, yeah, and phase number 3 will connect to phase number 2. So let's make another rule as well. We just copy that, yeah, and say phase number 1 will connect with phase number 0. So what we can do now is we can merge these rules. Oops. Merge them, and then also input them in the rule generator. And you see now, this is all the input the aggregation needs, but we don't see an outcome. And this is when you go on out, yeah, you see, okay, we have 26 input and we already have 26 output. So we need to get this part geometry, and we can do this with this component, and it's called get part geometry. Oops. And then we can just plug it in, and suddenly you will see the aggregation happening. And in this aggregation, it functions with our rules, yeah. So it means it always connects 3 to 2 and phase 1 to 0, yeah. And then you can just go up and down in the numbers. You can always reset them for a different aggregation in the end of the day, yeah. So, and this is now yeah, aggregating a component with itself. And to make it more interesting, we introduce a second component now. So let me just switch this to 0 again. And to introduce a second component, we will here in Rhino go in shaded mode again, and I will just extrude one of the faces. So here under volume, yeah, I will go on extrude surface and just create a prism out of it. Can move the prism somewhere else. We can also turn the prism that it's lying horizontal. We can also turn the prism that it's nicely lined. And automatically, since I generated this prism in one of the faces, it will always fit to the face. So let me get this off. And so then we can copy like our whole part, yeah? And we name the second part, we name prism, let's say. So, and of course, our part wants the geometry. This is something we have already. Set one geometry, and it wants the center point of the connecting faces and the direction. And since we have here the center points, I will also generate one on the triangle. I will do this manually now. So here to find the center point, and the direction should be the same to go one of the edges, like in the prism object, like in the other object. And then we will copy this to the other side. Just take it and copy it over here. So we, no, sorry. So again, select it. And we'll have it on the other side. And what we can say now, we can input the points, yeah, set multiple points. Point number 1, point number 2, press enter. So we have it, and set the curves, multiple curves, 1 and 2, or 0 and 1, press enter. So we have now a second part inputted. The second part we can then connect with our aggregation as well. And what we need now is actually a rule that says I want to connect my first part with the second part. So basically, I will copy this rule here and say it's not connecting octa with octa, but octa with prism. So octa 1 is surface with prism 0. So this is how I created the next rule, and I also want to connect the other way around. Maybe I want to connect the prism 1 with octa 2 and with also number 3 and with 4, let's say, yeah, or the 0 and 4. And you see with these rules, yeah, it can already get quite a lot of rules, yeah, but you have a lot of freedom how you basically define them. So now we have the rules, and let's see if something happens. So here you see now what we created is actually that sound like we have to move this guy a little away that we see better. So now we created like an aggregation. Oh, and see, sometimes it's not working, and this is because of the rules, and sometimes it's not given enough rules that this aggregation can work. So, and what you have to know is like it's always good to actually not connect in one side, which means like when you have surface 1 of object A connecting to surface 2 of object 2, you also have to do it vice versa to create the better connections. But what I will also show you now is a second way of generating rules. So we will disconnect the rules now. So here, disconnect. And there is under the rules, yeah, it's a more an automated process. There's something called the rule generator. And the rule generator basically automatically generates rules, yeah, from the inputted parts. And you can also set like toggles. So you can introduce rules that are connect the same part with each other, yeah, and rules that and rules that connect actually the same ID with each other, yeah. So the ID is basically the face of the part, and the part itself is of course the part itself. So what we can do here, we can of course introduce our part to the rule generator. We make whoops. Ah, no, a Boolean toggle. I made a box. Box. Boolean toggles are false. And we put them both on true. So the parts and the IDs are connected, and we put it in the rule generator. And now we see there are a multitude of aggregations possible. And you can also check it out, yeah, when the parts themselves do not connect to each other. So in this case, there's only so no same part in this aggregation connects to each other, yeah. So you have always the long element and then the prism-like element, yeah. When you set this false, and you can always test out what it means, yeah. Here the same IDs do not connect, and you see it already gets quite a different aesthetics. For now, I think this is quite nice. And what we want to do now is actually we want to tell Grasshopper to get separated parts out, because now when I click on the get part geometry, it always gets all of my geometries out. And we can do that with when we go to parts and we filter the parts by name. So this means we filter the part by name and then connect the part out here, but the part has no name yet, and we already have the name of our objects. Yeah, in this case, octa. Put the name in, And what you see now is actually that only the octa elements will be given out. Now we copy this one and connect it with the name of prism. And then you see this one only gives the prism out, and we can give it a color swatch and a custom preview. So, and to differentiate the two geometries. So as you see, now we already generated our first aggregation. So, and we had like two different ways of doing so. One is creating manual rules. The other one was a rule generator. Also, we will go deeper into the topic of the rule generator later. So, and what I want to do with you guys is also I will go into like these little exercises now and do one or two with you, so that you also can see how to exchange parts for a more complex geometry, for example. So the first part in Wasp here is basically done. Yeah, this is a little introduction, and it all functions very similar to the big file that I gave you in the beginning. So what I would do now is actually I will delete all of this. Oh, no, basically what we will do is I'll create a new document. So, and what we could do now here is actually, this is also something very similar. We go to the component 2 section, and this is in the file I provided you guys, also in the Grasshopper file. It's called poly, and now I will show you how to build that again. So it will be kind of a similar process what we just did, but I think a little repetition at the beginning to get to know the software is not bad. So in the beginning, what we will do, we will also and one more thing, here is already kind of a complex geometry inside a simple geometry. That means I will get the simple geometry out first. Yeah, let me hide this here. Oops. So, and we will start working with the simple geometry, getting the points and lines we need here as well. So basically this is the same body that we just had. So we can again take geometry, we can get our points, we can get our curves. So this is quite fast. We can then have our basic parts and create create the connections from directions. Yeah, here you see the names of the components as well. We connect everything again. We input the geometry, set one geometry, put it here on wireframe again. We input the points at multiple points. Let's say 1, 2, 3, 4. We make a point list that we see our points as well, and the order we inputted them, and then we input the curves in the same order, 0, 1, 2, 3. See the planes. Let's get the preview off. In this case, we connect here, we input the geometry into the part, and we give it a name. Yeah, in this case, we get a panel and call it poly. So, and oh, sorry, then the first part again, functions. And what we want to do in this aggregation is actually we do the same stochastic aggregation. We do a rule generator. We put the part into the rule generator. So, generate two toggles, put them on yes. Generate the rules, input the parts, input the number, 50. So here we go. And also let's check if the parts are distributed. Get part geometry and put the parts in. Yeah, and here you see, okay, it's working. And what we want to do now, what we have now is actually, yeah, an aggregation of our simple geometry. That's what we just did before. But we want to tell Grasshopper now to exchange every component with a more complex component. And the modeling for the component itself, basically what I did, I got the outlines of this component, and then I filleted the edges to create one continuous surface like this one, and then this surface is basically yeah, only scaled, yeah, with the gumball, and then created a loft in between. Yeah, so basically this is a very simple, yeah, very simple component. Just undo it again and gave it a little, yeah, nucleus as well, that it gets a little yeah, variation as well. Yeah, and what we see here now, okay, we have one element. Yeah, so this is the outer frame, just moving it a bit that you see it better. Then we have a second element, which is an inner frame, and then we have a nucleus, which is here. Yeah, I made this green. Actually, it's two surfaces here. And what we want to do now is we want to tell Grasshopper to exchange our component with this component. And what we do for that is actually we get a deconstruct part, or let's go up here. Deconstruct part component. Oops, it's a little bigger than that. So plug it in here. So basically, this is giving you certain attributes from the parts, and it's also giving you a transform part. And with the transform component, which we will get now here, this one, yeah, transform an object, we can actually exchange the original object with one of our new geometries. And for this, I input, for example, my frame geometry, set one geometry. Then I will commit to transform and the geometry here. Oops, what's happening here? Okay, of course it's not working since we have no parts. Let me quickly do the parts. And what you see now is that our frames are very wildly flying around. And this is because we use the transform component to transform the simple geometry with the more complex one. Maybe I give it a color preview as well. Check quick preview. Let's watch. Let's give it like a timber color. Something like this. And they are flying around here, and the reason why that is actually because the geometry we want to exchange, and the original or the base geometry the simple geometry are not in the same place. So basically what we have to do is we move them in the same place. I moved it with -2 so that they are on top of each other. And when I put the parts on again, start the aggregation again, you will suddenly see that they are not flying around anymore, but that they are connecting with each other. So, and when we make the preview on here, you will also see that they are now exactly on the base geometry. So, and what we want to do, we also want to get the smaller frame in, and basically every material or everything you want to put on a similar layer, you can input as the same in the transform button. So if I want to have the small frame distributed as well, I move it -2 and I put both as multiple geometries as my input. No. Check. Okay, it will not. Okay, it only takes one of the geometries. What I usually do then is creating a mesh from the two geometries, and then joining the mesh. So where is it? Mesh join to create just one object. And now you can see that, and it's actually also getting lighter. But now you can see the small frame is inside of the bigger frame. So I will get down the parts, and let's just have 3 parts here. And now I want to introduce the green core as well. So what I will do is actually I will copy the whole thing, use these geometries, input both of the geometries, place it as well at the core, and also put the color swatch to something greener like this. And maybe we will group it. So, and just that you have a little overview, we have the deconstruction of the part, then the transform component with the transform attribute of the part, and then the geometry you want to transform it. When you input multiple geometry, it's always helpful to make a mesh from it and to join the mesh. It makes it lighter, and you only have one object you distribute. And in the end, this is just for visualization, the color preview. And what you see now is when we go up again, we have like a more complex aggregation, basically similar to what you see here in the front of the file. So then you can, of course, play with it, test different aggregations and see how they will work together. When you switch this on, you have the original component. And then, of course, what is good now is you can always bake it. You would bake the transform component and always bake it to a separate layer. For example, so you will reach this, and then when you bake it to, I can also do this for once. We make a layer called poly component, and I make 2 sub layers. One is maybe wood frame, and one is green core. And I always try to give actually the material colors or the layer colors a similar color than the real material in the end. So it's actually in all viewports, it will look the same. Let's make this green here. So, and then we can bake the first transform to wood frame, maybe group it, bake the second transform to green core. Now I didn't group it, but since it's on one layer, it's all okay. We switch off Grasshopper. Let's see. And here we have the aggregation in Rhino as meshes. It's all grouped. Yeah, we have a clean layer structure. We can select it and maybe move it back here, our baked thing. And now I would also go to one more component, and maybe we take the weave component, or which one would be interesting. They all work quite similar, as you see. Let me just check which one makes more sense, or where I wanted to introduce something new for you. Yeah, maybe we take the weave component, then I can also show you a little functions or additional functions as well. So what we can do with that one is actually we create the custom rule sets again, or we create it in the rule generator. So what I will do quickly, I will take the first part of our aggregation and copy it. Go to the weave part. So this is here the simple part that we see, yeah, and inside there's a more complex element. So we input the simple geometry, set one geometry here. Of course, it will not work yet. Then we input the points, set multiple points, 1, 2, 3, 4. Press enter, and also input the curves. Now I don't have a point list visible. Whoops, sorry. So here's my point list visible. And we go to the curves, input the curves, multiple curves, loading, 0, 1, 2, and where's the 3 up here? So we have the curve input. We have the part. In this case, we call the part weave. That it's just for housekeeping. And what I want to do is like you have like what I created here. I go into shaded mode again, that you see this a bit better. Like a simple geometry that we opened up in the course. And what I want to do then is actually to make a smooth geometry out of it. Yeah, and a smooth geometry, then we can aggregate and create like a result that is looks quite organic in modeling. And to do that, we will go here. So we have the rule generator, which is totally okay. In this case, again, we have the geometries that are aggregated, and we want to again get the parts out. So we deconstruct the part. We want to transform the part, put in transform again, and put the geometry input in this one. So geometry input, get the complex geometry. Go back to wireframe, you will see it, it's already inside set one geometry. And I will make a mesh from it. Mesh. And what we can use now is, for example, we can use Weaverbird to smooth the meshes. Yeah, so we can, for example, use loop subdivision. Yeah, input the mesh. Put this one on 3. And we create, so what you will see, actually I get this out a little, -2. Don't know if this is very visible. We can always, if you want to see the faces of the mesh better, you can always get the face boundaries. And there you see that our input geometry is already much smoother in this way. And what I wanted to do with Weaverbird to get this thing, we take the frame component, picture frame, plug it in, create distances inside. Yeah, so we have basically it's opening up the meshes, this component, to create perforations inside of it. So we have something, for example, like this one here. And to get away like from the surface look and thicken it a little bit, yeah, we take the mesh thicken component, and this is of course a lot, so we kind of want to maybe thicken it and also maybe to the inside, so we make it negative. And then we have yeah, some quite interesting output, I think. Also put the preview off here, yeah. So I want to put this also create bigger perforations of it. And so basically this is how we created this component, and we can now put this one into the geometry exchange, move our component back to the original position, and then you will see that we have created something that you see on the other side as well. Can put the custom preview and the color, can give it a color again that it looks a little bit better. So previews, yeah, and then you see that we have created something that you see there in the back, which has a more organic look. And with Weaverbird, you can also, you have a lot of possibilities in variety to play with the parts, to play with the smoothness of the parts, and yeah, to create also like easy perforations and things like this. The other aggregations that are in this file, I will not like model them for now, because they are all basically following a similar principle. I will just open the original file again, and just for you guys as an explanation, again, like I said, each aggregation here, or each group is based to one of the aggregations. Yeah, for example, the cube. And what you see in each of these aggregations is that the aggregation itself is disabled. So when you enable it, you will kind of see the aggregation here, yeah, and then also can play around it. This one basically follows the same thing. Yeah, I have like a prep geometry input. I make a mesh from it. Yeah, I thickened the mesh. And then here I put also like a smoothing algorithm, in this case a Catmull-Clark algorithm on top of it, to make this geometry more smooth, put it in the transform button, and then aggregate this. So basically, this is follows the exact same logic that we just had in our weave component. So I disable this again. This one we did already here, and this one we also did with the weave component. Then the third one, this also functions very similar with the weave component. Like this is the lattice component, but instead of one part here, it has two that are then aggregated. Here I can also enable this, and also you can see that you can create like very defined structures. Yeah, you can also play with the lengths of each of the elements. Yeah, you can also introduce different lengths of the element and therefore create kind of like these growing spatial systems. Can always push like push the button here to reset the aggregation. And what we did here as well is like just we take out the parts with the name filter. We decompose the parts, yeah, take the transform button and transform the prep with the complex geometry that we want. Yeah. So also very similar in methodology to just what we did. And then there's also one more example. The last one, I think I called it prism. And let me enable this one. Yeah, here, so it's more like aggregation from discrete, maybe timber elements. Could be, yeah. So there's nothing new on this side, but there's one new thing that I introduced in this one. And there's another way to generate rules. What we already know now is basically the simple Wasp rule, yeah, where you plug in which faces of which elements you want to connect. Then we already know the rule generator, which is automizing a lot of these things. And what I did here is a rule from text. So basically, what you can do is I have here a pyramid component and a prism component. And each of these two components, let me zoom in here, has, of course, 0. Okay. Disable this. Each of this component has faces that are numbered in the way we click it. Yeah, like here, I make the number list, the numbers a bit higher. Yeah, which indicates their faces. And what you can do with the rule by text, you can create a panel and then just say prism, and then you do like this vertical divider, and then you say prism face 0 connects with prism 1, yeah, and you always have this here with a dash, connect them with a dash underneath, yeah, and this is basically just a shorter version of the manual rule generator where you have to plug everything in. Here you just say phase 2 from the prism connects with phase 3 from the prism. Phase 2 from the prism connects with phase 0, and so on and so on. And therefore you can create more and more rules. What's very important here, it's always easy to have some spacing here, like the rule generator, and this is what you see now, will suddenly not work if you have empty parameters in your panel. So always look out that kind of you end with your last rule, and then it will hopefully always work as well. So I enable this again, maybe put it 50 again, yeah, and then here you can also see quite a variety in design options you can do with actually quite simple input. And this is also the end of the first exercise, and I think we should always do like a 5-minute break between the exercises. I don't know, Mike, is there now also a time to answer some questions, or how do we do that? Okay, then I think we just do a 5-minute break. I will also.
Sounds good.
Sorry.
Sounds good.
Yeah. Shall I stop sharing my screen or shall I just leave it on? Because I would also open the other files in the background then.
Yeah, you can keep it on. It's up to you.
Okay. Then we see each other again in 5 minutes. So, hello everybody. Okay, so in our first exercise, I think we already saw quite some possibilities, what we can achieve, like what kind of different aggregations of spatial systems we can do. And let's say one use case we will do in our second exercise. I will just share my screen with you again to give a little intro to the second one, or like a little overview.
Hey, Marvin, I don't know if you want to take a look at the Q&A.
Okay, shall we do that?
Yeah, I mean, there's just 4, I think, small ones before you go too far.
Okay, yeah, sure.
Well, the one from Simon we can answer later. I think that's more like end of webinar, but there's the other ones we can. Like, is it possible to have a number slider instead of a reset button?
So that we could refer to an optimum solution by its associated number. What you like the question, like which reset button is meant? I guess it's the one on the aggregation.
I think so, and I think actually I think I saw in the in like the beta Wasp, they made like a seed value so you can like repeat the results.
Yeah, that's quite new or relatively new in it actually.
Yeah, but it's only in like the beta one, so I think it's still a bit buggy. But if you go to their GitHub, you can download like the beta Wasp, which has like some experimental features, and one of them does have a seed on there, so you can at least like repeat the results.
Okay, and then what's the next one? Here, why not use attribute component at the beginning? What is the advantage of using transform command at the end of the workflow?
I think Anders answered that, which I think he's right, because it like the high poly counts, like so it's better to do it like at the end, I guess, the transformation.
Yeah, I still don't get the question completely, to be honest.
Yeah, I guess it was like using a transform command at the end of the workflow.
Yeah.
And I guess that's because, I mean, that's kind of the workflow, is you define all the attributes and then transform, right? Like after everything's kind of defined. Which I think basically what I think it means is like, because you're aggregating like the simple units and then transforming to the simple units, the complex units, because you don't want to aggregate the complex units.
No, yeah, exactly. And because it would get very complex in the end of the day, with the geometry heavy in the end of the day. And like also the aggregation is built like this, that you always get the parts out later on.
Yeah, you want to work with like the simple stuff. Yeah, all right, that's it.
So in one with about urban beta.
Yeah, you can answer it now if you want.
Done in Grasshopper or Wasp. Partly it started, but then later the construction files and all of this is done manually in Rhino, and then also in BIM software later on. Okay. Cool.
I'll let you keep going.
Good. Then there's here's just a little looking back what we just did. Just rendered a little bit nicer in Enscape, but this is also something we will take a look at later. So next slide. So I just put together some inspiration, and also in the folders or in the Dropbox that's prepared, you will find like a lot of aggregation-based design pictures. I think I put like 100 projects or something in there, just that you also can see what is possible with it. Yeah. And there are like also nice, also realized examples around around the world, where you can always see it propping it up, be it from TU Munich here actually with Moritz, or Jose, this kit of part units, for example, or in the middle, I think there are some components from Jill. And just that you see like also how we use it sometimes in our research, like you can connect it with different software. You can go free, like here, like just like drone distribution, augmented assembly. This is also something that we tried in the beta pod for the first time using AR on site, which was actually quite good and easy to use. And also gave a good impression for clients as well, because they could also have a virtual tour for the pod. And now coming to the second exercise, and I called it urban mining. So the application of the exercise will be like something I think that's quite important topic at the moment. So because like the AC industry, 60% of the CO2 emissions are by the building industry. And we also have to learn how to use the waste that is produced by the construction industry in more efficient ways. I think a project that's already a couple of years old that showed this also in a very artistic way. It's called Mind the Scrap, where basically the idea of the project is to recontextualize, to scan construction waste and then recontextualize it via computer algorithms. Like the computer defines the final outcome of this. And also in the exercise, it's a little combined with the topic of urban infill. Also in the office at the moment, we are developing workflows to scan cities for potential plots that are not developed or that are in development, or in different attributions, that we can create business cases for temporary architectures. In the exercise itself, we will look at components again, and also exchange simple components with downloaded components this time. And I think the components themselves, we downloaded them from Quixel. I think it was a bit ago, to be honest. But there you will find also like high resolution objects. For example, these are like steel connectors and like I think a curb from the sidewalk that we will just use to make an urban infill. And also we will introduce a new aggregation method in this exercise. And this is kind of like the field aggregation. Now we had the stochastic aggregation that always grows from a single part in all directions. You can also later define it a bit more. But in this case, what we want to do, two things. And one of them is aggregating a volume. So creating a field around the volume and aggregating along a curve. They both function very similar. We see it in the bottom actually. So we will create kind of a bounding box around it and create different voxels inside, and then we will basically measure the distance from the curve to each voxel to create this field. So basically each voxel has a number value. And this is the lower right picture from Andrea Rossi, the programmer of Wasp, who's also a big supporter in some projects. And basically, I think the graphic shows it very nice. Like for example, like with the highest number value, or in this case would be red. The first parts will be aggregated, and then it looks for the next number value to aggregate more parts. And so then later on you can aggregate these fields or along curves. And what we will do is to create something like this, like an urban infill. And to start with this, I will switch to Rhino now. And you will find this when you open exercise number 2, mining, then you will find the Rhino file. In the Rhino file, you already see an example aggregation here from these elements. Put it on shaded. And you see, yeah, these little brownstone houses and like this urban gap that we are trying to fill. And we are actually trying to fill it. What we want to do is actually create in one part a geometry that we want to fill that fits inside of this gap. Yeah, in this case, I think the geometry itself is just like a simple donut with the polypoints on. You're very free in creating whatever you want. Yeah, especially in Rhino 7, like you can with the sub-D modeling. Yeah, you can create easily good and complex forms. Or don't have to be complex, and then yeah, fill them with these aggregations. Second one is a simple curve. And what we will do, we will use these components, and I will open this in a new file, and then we will create it from scratch again. This is just that you see it once. This here is how to build the field on the volume. This here is how to build the field around the curve. And this up here is basically the aggregation, the creation of the parts, aggregation itself with the rules, and then getting the parts out again. And then down here, this I will also go in later. This is just a little helper tool with the curve aggregation, so that you can also see in which order the parts are aggregated. So let me start a new file. So what you see here already, yeah, these are on the right side, these are the simple parts. You can also see already that I prepared the center points and the directions already on these parts. And this here is, and this is the difference to the last tutorial, because this is geometry that is just downloaded from an online platform like Warehouse or Quixel or something. And can also go on render mode. Then you can also get a little better impression of these. Always takes a while. Let's wait if it's coming. Here it is. So these are kind of like these steel beams we downloaded, and here this is just like a simple curb from a sidewalk. But this is also just to give you an example that you're not limited by your own geometry, but that you of course can use a variety of geometry. So we do the same stuff again. Yeah, so we will create 4 parts in Wasp. So I will try to quickly do this. I will also switch off my video during it, so it's a little bit, hopefully a little bit faster. Oops. Create like a simple part, and so just see what's going on. Create the point list again. This is a little bit repetitive. We call the panel. We call the first part. We create a panel, and we will call the first part cross. The lowest one you see here, just put it in cross, give it a geometry, give it a connection, the points, point list. So I will input the cross geometry, put it on wireframe, input the points. 1, 2, 3, 4. And put the curves in the same order. 1, 2, 3, 4. No, this one. So, preview of. We will copy the whole thing, create a new name for it. The second one we call just long, because it's the long bar. You feel free to choose your own names. Yeah, you can name it however you want. We will input the geometry again. We will input the points again. 1, 2, 3, 4. And we will input, the curves. 2, 3, 4. So now we have that input. We'll copy it again. Maybe group it. So, and it's called the third one like angle. Let's say because it's an angled element. Get the geometry in again. Set one geometry. Set multiple points. What do we have here? 1 and 2. Set the 2 curves. 1 and 2. Press enter. Then we have this one in, and we do it one last time. This one we call a curve. Was this other element that we were seeing, so we put it also here in the geometry. Set one geometry, set set multiple points, 1 and 2. Set the 2 curves, 1 and 2. So we created our simple parts all together. Maybe we merge it just for the housekeeping, make it simpler with the connections later. So here, merge, so we only have to connect this one in the end. And now we go in aggregations. And till now we always did the stochastic aggregation. This time we will take the field-driven aggregation. Yeah, we will input our parts. This is the same thing. What's different here? You basically have the same input. Yeah, we create the reset button. We create the number of parts. We create the rules with a simple rule generator where we input the parts as well, and then create the rules here. So, and the difference with this one is just that we see that it wants an additional field. And this is something new we will create in this exercise. I will also put the get part geometry on this end. So what we will do, just like explained in the little intro before, what we will do, we will create kind of like these volumes around our curves or around our volumes, fill them with voxels, and then get the measures towards the points, if the points are inside the volume or outside the volume, or if the points are in proximity to the curve. And to do that, let's start here. First of all, we will start with the geometry one, or with the volume. So let's get the geometry in Grasshopper, set one geometry. And what we will do here now is like we will use the field points component. So put the geometry into the field points, create a slider. Oh, sorry. Create a slider with 1. So here, this is the resolution. So maybe we need, oops. Oh, sorry, it's like stuck with me here a little bit. Oh, that of course shouldn't happen. Like the field is usually quite computational intensive, because like you create kind of like this big resolutions, and now I did like a little error, and hopefully it will solve itself. But what you guys see already on the left side when you look at Rhino, yeah, that kind of like these elements are aggregating along the volume. And just right now, I'm really hoping that it doesn't crash with me and it will stay with me. That sometimes happens when you put the wrong thing in. Okay. Okay, I'll quickly restart the file. We're not that far into it, so I think it will be quite fast to do that. In the meantime, yeah, you can already also create your parts, yeah, also like everything that we learned already, like maybe also create everything with the transformation after the aggregation, because this is also something where we will get then our complex parts later out again as well. And now you have to stay with me for a minute until the file loads. Here we are again. So. And we're back. So I will make a new document, but I will copy some stuff that I just created. I will just copy it from here into our other document. And now we can start creating the field again. So again, going back to Wasp. So we were here in creating the field points around the field. Yeah, that means we need geometry. We need resolution. We'll keep, I think, in this file the resolution to 1.0. Then input the geometry as well. Genau. And what we will do now, we will take the pull point component. Oh, wait, sorry. We will take the pull point component, yeah, and we will measure actually the distance from the geometry to the field. Yeah, what you see in here is already it generated these points on the field. What we need then is, oops, we create some bounds where we put the pull points in, and we want to remap the whole values of it. And I just realized that maybe for you guys it's better to have the bifocus on, so you can see also like the component names and everything. So here, so we have the remap components. So we put a boundary into the remap to enter the source domain, and the original value from the pulled point. And we are doing this actually to create the Wasp field, which will also wants to have a name. Sorry, put the panel in, give the Wasp field just the name, field 1 in this case. Doesn't matter so much how much you name it. And with the remap volume, actually, we will also apply a graph mapper. And the graph mapper, oops, we put the zero graph inside. And we do this actually because then we can actually have a little more control over the volumes of the field. And here, in the end of the day, we created a field from the points, and we input the values. And to visualize the field a little bit better and maybe make it understandable a bit better, we can also deconstruct the field here again. So basically, when we have the field, so this is what is created, the bounding box around it, and then you see kind of like the pulled geometry on the volume. And what we can do here is also we can make a custom preview, put points in, and maybe create a gradient to make it more obvious in a visual way. So let's get the gradient from green to red. We put in the values into the gradient, and then we can actually see what's happening inside. Let's get here, let's make it a little bit more visible. And here you see already the points that are pulled on the geometry. And now we also with the graph mapper, we have now some influence, like how strong or not strong basically this field will apply. And the more it goes into red, the more likely we will see the components to be aggregated. So it will always start from like a red side, where the values are higher, the values of the distances are higher to the box, and then aggregate to the lesser red, yellow, and green components. And so we have we have actually created the field around our component. I put it off again. And what we can do now is actually we put it into the field component, into the field aggregation, and then check about the outcome of the parts. Just put a simple get part geometry for now. And there you can see already that the elements, the different elements are aggregated inside our volume. No, maybe this is here and ghosted. You can see it better. And if we put like the number up now, 350, for example. So let's see, you see that they stay inside. We can also actually put it up a little bit higher in this case, because we're not changing the geometry yet. So let's give it 1000. This, of course, will take a little bit. So, and here you can see, like the more components you create, they will actually aggregate inside of this volume. Which is actually kind of nice. You have a lot of control of the volume itself. I would just advise that you maybe disable your geometry before you change your volume. What you can also do, you can always create a different resolution of your field. which is a possibility. But in general, like the voxel size of your field should like correspond with the components in your aggregation. And what we are doing now as well, of course, we want to exchange the simple components for the more complex components. And in this case, like we will do the same thing then in the last tutorial. So basically, we will filter. Oops, sorry. We will filter our parts by name, and in the end, we will do this 4 times. You can either connect the original name to the name here, and then we can also transform or sorry, deconstruct the part again. Let's do it up here so it's easier to find. So here, deconstruct, then we put a transform on and input the mesh, the downloaded mesh geometry as our geometry. So actually we're in the first part, the cross, which would be then this one as the complex part, set one mesh. And now you see the same problem that we had before, yeah, with the flying around components. This is because the complex component is not in the same position as the simple component. And to do that, we of course only, oops, it's indicated here, move it by, it's not true actually, we only move it by 10. I accidentally wrote 20 here, so maybe we wanna correct that to 10, and then the parts are in the same positioning. So we do that, copy this component again, connect another name with it. I think in this case, I will just copy the names over here. I think that's a little bit simpler, and connect the name like this. So, again, copy it, filter by the name. So getting a bit messy, just seeing that we have enough space, and then we have to see this component is apparently not used in the aggregation as it is right now. Then we check the meshes, apply the complex meshes to our aggregation. Yeah, here again. Now you will see actually the flying elements again because the elements are not aligned. Now we have the cross, we have the long. Let's do the angle as well. Set one mesh. This one is here. And even though it's not used yet here, you can also still here set one mesh. And then we have the right transformation attributes. We will move it over to 10. So you see that we're back inside of our aggregation. Just to make it faster, I will go down now from 1,000 parts back to 300. And that, of course, takes a little bit of time for computing it. So we're back now. So maybe refresh the aggregation as well. So what we saw already now is like how to aggregate the field in this way. We also want to do it in a second way. We want to aggregate the curve function, or we want to aggregate along the curve function, which is another possibility. It functions very similar to the first one. So what I will do now here, I will deactivate or disable this field. maybe also disconnected. Oops, not here. Disconnected, and I will just move it down because we will concentrate now how to aggregate along the curve, and for that we will build also another field around it. So the first thing is we get of course the curve into Grasshopper, set one curve, create a bounding box around it. So bounding box. So I will zoom into the curve now. What we actually need here is just like the volume component, that we get the center points out. What we want to do and what is very helpful in the field points when you work with curves is actually that your bounding box is a little bit bigger than the one that is just created around the curve. So this is why we want to scale it. And this is also why I put the volume here to get the center point of the bounding box. We take a scale NU component, put our bounding box in here, yeah, and then it wants from us, of course, the scaling factor and the center point, which we have here with the volume component. And let's say we scale it 1.2 in X direction, 1.2 in Y, and oh, no, let's see, and maybe 1.5 in Z direction, just to make it a little bit bigger than the original one. So, and give it a little space in it. So then again, very similar to the last field. Yeah, we get the field points. In this way, this time we connect our bounding box with the field points. We create the resolution. Again, let's take the same one that we had in the last field, which was I think 1.0. Then try to measure the distance, and this is important. We try to measure the distance between the curve now and the field points. So we put in the field points, and we put in the curve bounds. Then again create some bounds, just like in the last step, where we can then remap our numbers here, setting this in and getting the graph mapper again with the this is nice. Let's put it a little bit to this side, and we create our field again. Yep, here we can name the field, of course. Again, type in the panel curve field. So it's not necessary. Get then our field points here from our field hours, and then we create also the values where we have more control with the mapper, and also to visualize the field again. I will just copy the components from the other fields up. Just a little down here, space. So, and then you can take a look at the preview, what you can really see in this case when I put everything out here. We create a field around the curve, hopefully. Let's see. And then we connect our fields with the field component, so, and reset it. And this will take a while. I put this preview off again, so we can see actually what happens. there's something happening with flying elements. Okay, let's check it out, why they are not connecting as well. Oops. So here, let's see. So this is our field. So, and basically, this gives you just an overview, yeah, how we create these additional fields. And I will just go back to the original file. In the end, what you see also in the file is here the volume-based aggregation. So basically, this is exactly the field that we just built around the volume here. And you see the curve-based aggregation. Actually, I put it on here. And there you see also the distribution. This is something that I added. I mentioned it in the beginning already. When you have the different field, yeah, for example, here is the curve field now connected. Yeah, the field that we built around the curve. Yeah, you see creating the bounding box around it, scaling it, creating the field points, then creating as well the curve field with the remapping. I think this was something I forgot. I didn't remap from 1 to 0. It's also why it was a little messy. Then creating here the aggregation again, and then you see also when we put like a higher number into the aggregation itself, and you should also see that actually it will float along the curve here quite yeah, smoothly, let's say. And also on the right side, you have your output and your exchanged elements. Yeah, all the elements are now lying on the basic volumes. And then just one thing that I just unmarked right now that I wanted to show you is actually how you show the growth of the field. So maybe I will just show you in live how to model it. What you need there is actually you create just the output of your parts. Yeah, in this case we have 500 parts. I put it maybe a little bit down again that we get faster. So 240 parts input. Yeah, we make a list. We make a list with 240. Create a range here, and create the part, get part geometry, get part geometry component. Yeah, so we get our geometry out here that we kind of see this right now. This is doubling it, but so we have the elements actually and the range, and what we can do here now is we can put the gradient into our range. Yeah, whatever, let's make it green, dark green to light, and we can put a custom preview into it. So we just put our geometry in, maybe hide everything else here, which could be distracting, and put the preview in this. And actually what you see in the preview is now, since you have the range, you see the darker it gets, the earlier the part is distributed. Yeah, also that means that where it's here, it's really dark. These are the first parts, and then it kind of goes out from there. And like the more yellow the parts in this aggregation are, the later they are assembled in this file. And actually this brings us also to the end of the second part the end of the second exercise. Yeah, so this was the exercise that looks at urban mining. with an infill element. Of course, you can then bake your elements just as we described, yeah, on different layers. You exchange it with the complex elements, and then also take, of course, the texture from the elements, so you can place them like here in the file in between the buildings. You can play with the volume later on. You can create different volumes, and you actually can have like a lot of control of your fields. And so, and there I would say we go into another break, and maybe after the break we can also answer some of the questions again, and let's have like just a 5-minute break until yeah, let's say, or let's make until 5:30, and then we see each other again. So, welcome back, everybody. I hope you guys can see me. Also, the sun is also already vanished here, so it's got quite dark. So it's 7:30 in the evening in Berlin. We wanted to start actually with the Q&A again. So I will also share my screen again, and then open the open the Q&A field. It's not exercise related. Yeah, we did some courses at the Bartlett to answer that question, and yeah, Jill is a friend of mine as well, and yeah, he's leading the B Pro unit there. Personally, I was not involved in his pavilions, but we see each other like from time to time, if that answers the question. Are there any other questions from you guys regarding the last exercise? Okay, I didn't see any questions coming in, so I will just do a little recap. Yeah, what you saw, we had in the last exercise 2 options to generate field, to generate more precise aggregation. One was based on a volume, and the other one was based on a curve. Which are actually like 2 good ways to aggregate things. Our scenario was this one here, yeah, like an urban infill scenario, and we used kind of like this downloaded geometry parts, or like some elements from streetscapes to create 3-dimensional structures and aggregations as well. The third exercise will combine 2 different things, and we will talk, or what we will create in a, yeah, I think a little bit more playful way. Yeah, there are also a lot of other ways, and also like, let's say, more intrinsic and more correct ways to create funicular structures. Yeah, like structures that are arch structures that are formed by optimal load bearing, that are formed by physics, usually creating void structures. And like I just had a little bit of background on this as well. Like what you see depicted here are the hanging models for the Sagrada Familia from Gaudi. So it's a very old technique, yeah, to create like these vault structures. As you see on the pictures, like Gaudi created them upside down, because it's always kind of like the optimum load bearing that is created by gravity. And when you turn it around, you create like an arch that is very good as a load-bearing element. This was, of course, continued later on by Frei Otto. Here are some pictures of like the soap models that they did, minimal surfaces in Stuttgart, also creating kind of like a lot of these advanced hanging models, creating these roofs with minimal structures. The last one where is involved, of course, the train station now in Stuttgart, and one of the biggest one in Munich realized the Olympia Stadium. Yeah, this is a picture of Frei Otto with one of these wall structures. That's, for example, also realized in the Multihalle in Mannheim. That will be restored now, thankfully, and not destructed. And to create like kind of like these three-dimensional structures, this will be a small part of the next exercise. But what we will do then is actually we will not stop there, and also not 100% like physically correct walls, but just to introduce like a little voxel-based strategy that allows you guys also to play around and generate easy forms along that. As said, this was just a little workflow we created, I think, a year ago, just to have fun, and not saying that kind of like these reference projects like here from the Block Research Group or from Mark Forns that kind of use, of course, way more advanced methodologies to create kind of these structures. Yeah, also these like strip methodologies to create complex geometry and these wall structures. Some more examples here by Foster, and also this is where we will start the journey with this exercise. We will mainly focus on what's depicted here in the upper part. I think I have a little zoom in here. So basically, we will create a pixel pattern, like a 2D pixel pattern, which is like super easy to use, which is super easy to manipulate and to transform, which you see in the second step here. And then we will, with Kangaroo, we will apply forces towards it, so that we are creating void structures from it. And more like in a, let's say, a little bit more free workflow or experiment, we will populate these void structures with components, basically using the strategies that we already applied. That means we are creating curve fields, or we are creating a field around this funicular or these void structures, like generated from the mesh, just like we did in the exercise before. And then we come like from this simple vault to an aggregated pavilion, which we see here on the left side. And let me quickly go into the file. I will exit the last exercise and go into this one. Let's see. Okay, and just for you guys to get an overview, like in the Rhino file itself, you see like these 5 little steps. Actually, we don't actually need these 2 steps up here. This was also like a tryout we did like internally to find out which is the best way to populate these structures. I will quickly also introduce that to you as well. But also the simplest way is actually to take then the original mesh and not extract these curves to populate it. And here, as you see in the first step, it's really like just a grid from 2-dimensional pixels, and we can transform it as much as we like, and then apply forces to it. And this corresponds, basically these first 3 steps correspond with what you see here in the upper part of the script, which is first of all the input of the voxels. Then we create a mesh for from it. We define which volumes Kangaroo, like the physics engine, needs. This is the physics engine, this bouncy solver, and then also output the mesh from it. And then we arrive at something like here in orange in the script, and then we will aggregate, and then we will start aggregating it again. And I will also switch to a new file, but I will also occasionally switch back to this one because just to avoid repetition with the last exercises, especially when we go into the aggregation part, yeah, you will see a lot of things that we have done before. Yeah, I will introduce you to the elements, then the fields are basically similar to the exercise we had before. Also the rule aggregation and the transform to get out the components. This is something we know already, but we will go through it together again, just to keep it better in mind. And for the Kangaroo part, I will open a new file that we do that together. And let me just adjust the window here a little bit. So, and basically what we did here, we just thought of really like how can we make this accessible? Yeah, like to create like a funicular structure like this, or a void structure like this. And we came basically up, why don't we just use pixels, because it kind of fits to our aggregation methodology, or like this voxel-based methodology we use a lot, and actually use these pixels in this case in a pavilion size just to basically paint something on the ground. Yeah, so you can basically take them, arrange them in an order you will. I already did it. I already did like an order here. What I did like this, maybe you could define it as 2H icons or something like this, like with a bridge connector. And the reason for that is actually I just want later to create kind of like these little feet of the void structure and see how it comes out. So, and what I will do is actually I will take this and just copy it maybe a little bit over here. So, and make another copy that you also see the step-by-step process. So what we can do now is actually we bring all these surfaces into Grasshopper. So let's see, here we are, and then we make a mesh from it, just a number of subdivisions. In this case we put 3 in this file. Yeah? So basically your mesh here gets like a little higher resolution than what we had before. This makes everything then a little bit smoother. Then what we have right now still is, of course, we have like all these single pixels. This means like every pixel in here is still one mesh. They are not connected. And this is something that I want to change now with the mesh join component. And we click here, like we see that we have one mesh now. That we can from here on, of course, use, but the mesh usually when you join the meshes, they are still they are one mesh, but the edges are not joined. And if we really want to do this, yeah, we weld the edges as well. Oops, together. So to have this here, and what we want to do now is actually we want to create in Kangaroo, we want to create like this physics engine. And for that, here, like this is what we mainly use. Yeah, like we will create a bouncy solver. Yeah, this is like visually quite nice way to represent the physics. Then we will, and it needs several input. Yeah, it needs several goals. And in this case, we want to define anchor points. which means which I already put here on the sides. Yeah, like you see these little points. And this is the anchor points will be the points where when the forces are applied to the mesh, like this will be the ones that are the anchor and stay on the ground. So let's get these points as anchors into the definition. Yeah, select the points, set multiple points here. Okay, so we selected them, input them, and basically in Kangaroo is like every of these goal objects. So everything of these forces you want to apply, everything comes into the goal object input. Then what we want to do for sure is we want to create different loads, like a vertical strength that pulls. And what we will do there is for sure we'll type in vertex loads. Yeah, and as you see in the icon already, this is basically a force that will pull either down or up in our case. Sorry, and I just put here the names of the components on again so that you see it. Yeah, so this is the second goal object that we want to do, and it asks us for our mesh, yeah, that we put in our original mesh. And what you saw already here in the definition is that the forces pulled everything down. And if we of course want to see that again, we create a button for once, and also a toggle because I wanna switch it actually off for now so that it's paused. And when we have it on, we can always reset the solver, yeah. So you can always start seeing the physics. So basically what happens now is it's pulling, the gravity is pulling the points down. And we like want, of course, for once we want to pull it up. In this case, I'll make a number slider with 0.57. So what you see now is actually that it goes up because it's a positive value. We have the anchor points, then we want to define the edge lengths of the object. So, and this defines how much, because like when you apply forces to the objects and when you have the anchors as well, you will also have, like with the edge lengths, you will have a certain attribute how much every edge can be stretched. Yeah, it's like when you have a fabric and you pull on both sides, then you can basically define how strong your fabric is. And for that, I will put 0.50 in the length factor. And what did we put here? We put, let's not copy it. Put 8.1. No, 8.1 in the strength. So these are just factors that you can also change, of course. Yeah, like how much the strength is, how much the length factor of the different edges will be, and the pulling. And what we will also insert is a show icon, and then we connect everything here. So with the bouncy solver, I will also connect in the output a mesh. And now what you can see is actually we have the anchors inside. So basically our mesh will stay on the ground exactly at the anchor points. Then our mesh already has quite a nice resolution, I think. And we have a certain X length and limitations in the length factor. And when I change this, for example, you can also immediately see that the mesh shrinks together. Yeah, and when we put it to 0.8, then our edges can be longer. Yeah, and it can be stretched further, and there you can play with these different strengths, with these different lengths, of course, until you find a form that you're comfortable with. Of course, you can also change here the vertical loads on the whole thing. And what was quite cool for us with this pixel logic is actually like what you can still do is you can change the original pixels. Yeah, in this case, I just put the points on. Of course, oops, take also the anchor points with me, and then I can just pull out the foot wherever I want to have it, for example. Then I can, where is the, now I can put it together. Yeah, like I can change where I want to have my feet. Yeah, sometimes then you have to, of course, press the reset button that you generate then a new mesh. Yeah, and so you have actually a quite simple tool, let's say, with quite some freedom. Yeah, and also an easy way to, let's say, paint something on the ground and create kind of like a three-dimensional structure from it. Yeah. So, and yeah, now we can say, for example, okay, it's the mesh. That's the mesh I like. Let's bake it and continue with it. I just will bake it on the default layer now. No. So wait. Put it off. It's slower. Here's my mesh. I think I baked it twice accidentally. So let's just take it out. And from here on, so I will just do a little recap of this like very small like Kangaroo setup. So the first thing we have is actually our pixel aggregation. Yeah, you can design this as in whichever configuration you want. Yeah, you have a lot of freedom, and you're also not limited when you once start the solvers, that you have still freedom. I can move my foot 2 meter left, 2 meter right. I can make the foot smaller, bigger, and create like a funicular structure, like how I want to design it. Of course, we could make this everything here smoother, but since we want to aggregate our components on this structure, I think it's enough to have like rather a very simplistic model, let's say, that is based on the anchors, that is based on the edge length component and on the vertex loads here. And then I would say I just quickly jump back to the original definition. So what we did now, we did the whole upper part, so the Kangaroo part, to generate the geometry, and the lower part is then again like the aggregation part. So what we can do for the aggregations, I will just jump back here to the original mesh, is either we take the whole mesh and create a field from it. And what is prepared in this definition already, this is, maybe I delete some of the stuff here. And maybe I also move this mesh over here. So what we want to do is actually, yeah, we have this mesh as a basis, and we want to generate aggregations on it, yeah, that are in the result and something that you see in the picture here. For that, I prepared already yeah, 2 elements, like one connector element and one timber stick. So as you see, the timber stick is just like the simple element and will not get exchanged. And for the connector element, this is like a bit more complex. Yeah, for example, could be like a 3D printed from metal or something like that. What we kind of do with these 2 elements, we generate again our parts, and this is completely the same way that we did it in the other tutorials. Yeah, so basically you basically set your connection points. Yeah, you set your direction curves, and then create the connection, and then create your part. You name your part. You do it once for the timber element, which is this one here, and once for the metal element, which is the one on the left side. The 2 things will be merged and then fed into the aggregation, like we did it like now in the examples from last time. There's a rule generator, so this is also nothing new. And on the right side, you will also see the name filter, yeah, wood and the metal part is then exchanged. I will put it just quickly back in its original position. And then the simple geometry, which is here, is then exchanged to the more complex one with the transform button. And when I click enabled on and enable the aggregation, and let me quickly check which field is in here. It's like the mesh field, so maybe we set one mesh. So, which is basically here again the same definition for the field with the bounding box, creating the volume around it, then scaling it a bit up, pulling the points and measuring the distances. Yeah. So basically, this is exactly the same thing that we saw before. We see here the aggregation, yeah, where the points get red. This will be the fields that will be aggregated. As firsts. Now, putting the preview off again. Then the field is connected with the field aggregation, of course. The field is connected with the field aggregation, and then in the right part, the geometry again is replaced with the original geometry. And now I just have to put reset here once. And what you see now is actually, yeah, we have the field around our geometry. These are the 2 components, yeah. The component 1, which is the metal connector, component 2, which is the stick, which make, yeah, some, actually I think the color is exactly the other way around in this base, but now we can also see, yeah, if we put like a, I don't know, let's say 600, and then we can see how our components are aggregated on the surface. Yeah, maybe I go a little higher with this one. So let's see. So, and as you see, yeah, the more and more components we have, the more it grows along our original surface. Maybe I put it once to the maximum. So it takes a bit. So here we go, yeah. And let's see if I can still move around in there. Yeah, just takes a while, yeah. And then where I think these ones are, it's just a little more components in the end of the day, but you can already see when we hide this one, that actually the structure now completely follows the surface and creates kind of like this walled pavilion, which is quite a nice structure, and it's kind of a superimposition of kind of yeah, minimal geometry optimization, and also component-based modeling. In the end of the day, I think we should also bake our structure into Rhino. I will just make a new pavilion layer. Give it two substructures like the connector maybe, and the timber stick. Making the timber stick brown, making the connector rather dark. And then you see it like the two name filters, yeah. Here the timber stick can be baked. So let's bake it out. And here maybe we do this. And the metal connector, we have the transform, yeah, with the complex geometry that is input down here. And then we put it on the connector layer, maybe go out of Grasshopper again and just see the whole geometry inside of Rhino. So here we go, and there you see basically ready to render. We can, of course, later we will take the structure also and put it into Enscape and yeah, create some more realistic visualizations from it. For now, we keep it, I think, with the Rhino view. And here, just that you see the result again, yeah, on the two layers. I think now it's overlaid with the Grasshopper file, but it gives quite a nice ambience in the end of the day. And so let me go back to shaded mode. If you actually are interested in a certain growth over the structure, this is also something that is inside of the definition. This is here the curve field, which is the same curve field that you had in the last exercise. And what we did with this one, we were just taking a mesh, so our mesh here. Let me check, maybe I got him. Check our mesh, input it in Grasshopper. Maybe I will just quickly this to 200 again, that everything is a bit smoother. Then go back to our mesh geometry and look for a component that is, I think, also in Kangaroo, that's called Weaverbird. And basically what this component does, it can give you the mesh curves in like A and B direction, or like in a U and V direction, which means just check this here. So when you see now the curves, so these are kind of like the curves from left to right. When I click it in the A, then I have the curves from up to down. I could, for example, bake the curves now. Just put it on the timber layer. Taking the curves. And so there's like a manual step, because what we wanted to create once was also that kind of when you see the growth of your aggregation over the pavilion, that you have like a certain direction. And what you can basically do is in this one create one curve from it. But for that, maybe I delete some of the wait. Not joined. First, we join all of these curves and take some of them out. We don't have to work too much. I will just delete some of these curves here. Maybe also some of these curves here. And what you can do is actually connect all of these curves together, basically make one giant curve out of it. So, of course, not necessarily the physical correct way. There's also a little bit of handiwork involved, but what you can then achieve in the end is actually like a growth from left to right. So what I will do here is just connect the ends, that it's one continuous curve going over here, going back. Maybe we don't even need these two. Maybe. So connecting this one, connecting back here, and this we will just quickly repeat with all of the ends until we are back at the second foot. So here we are, and this should be the last one. I think on this one I wasn't very messy. Just move this away, and then hopefully have one open curve. And this again, I have copied here the curve-based aggregation. Sorry, this one down here, yeah, the field from curves. And I will just input this into my field, and then it can calculate the field from it, and then you can also see how the aggregation grows along the curve there. So it's just two different ways, like just to populate your geometry. I think the first one is smoother and works also a bit better, also without the handiwork. I just wanted to show you the second one as well. Of course, we have to connect our field then again and see how the elements are populating the curves now. Yeah, so this is also like a little repetition again from the last exercise, so you get like firm and comfortable with both of the ways to aggregate. And that brings us also already to the end of exercise number 3. So we combined Kangaroo physics with Wasp aggregations, created a funicular structure, a vault, pavilion, you might say, and then used 2 different elements to aggregate on top of the structure. We saw 2 different methods how it could work to generate a geometry and a pavilion like that. And I would propose that we do another 5-minute break before we go to the next exercise. And when we start with the next exercise, You also like maybe use the 5 minutes if you have some questions or some feedback. I will happily answer everything, or I will try to answer as good as I can everything that's coming in. And see you again in 5 minutes. Okay, welcome back. I hope most of you are still there. I would say we would begin with the Q&A. Let me share my screen again. Sure. So, okay, there's a question from Nima. The problem is that the components are aggregated based on some random criteria. Do you have the control to aggregate them in a meaningful manner? I think part of the question was already answered by Mike in the beginning with the beta mode of the aggregation modes. Yeah, that you can put seed values inside and that you have a repeating aggregations. The second thing is these exercises that we're doing is not advanced, so we will rather see architectural applications for the aggregations that we learned already. And this is also what the next two exercises is, but there are a lot of constraints you can put into the components. For example, you can put constraints that you have no more cantilevers, that you have support structures, yeah, that you have realistic load bearing, that you have orientation constraints. You can put mesh constraints in, yeah, you can define fields that are not aggregated. You can also, with advanced parts in Wasp, you can also like orient it. You can also very precisely aggregate on surfaces, for example. Yeah, you can also define how the surfaces, or like in which order the surfaces are defined. You can create hierarchies in your aggregations as well. And then, for example, you can like then create denser and less dense field. You can create yeah, basically gradients. Yeah, that like some areas are more populated with one component, some are more populated with the other component. So there's a lot of possibilities and restrictions you can put into the script as well. And therefore I would really recommend Andrea Rossi, who was also supporting us in some of the workshops lately. He's the creator of Wasp, and he also has actually, I saw on the YouTube side, he has some new videos of new constraints and of new features of the new version of Wasp. And that would be, I think, quite interesting for you, Nima, to take a look at, because then I guess I try to understand what you mean with the randomness. Yeah, like you press the button again and then everything is somewhere else. But this is also on one side features that are working on right now, and of course a lot of constraints where you can also give more input in or like more control in the aggregation you want to have. I hope that answers it. Then the second one, how can we go through the fabrication process for such complicated structure? I don't know if you mean the pavilion structure, for example. I think which is in the background right now, since there's probably a good way of labeling what we did in the past. There's which is cool for aggregation, especially if you have like an iPad or a HoloLens. You can work with AR tools. Now I forgot the name of the company. There's an AR plugin called Hologram, I think it's discontinued though, but it gives you, basically you can create like an AR manual and see where every of these parts can be placed, and then you can place the next one and can place the next one. And tools like this can also like quite help on the construction side in the future, for example. Genau, the next one, I think that's still the same question. Then question from Camila. I'd be interesting to see that type of aggregation applied to a minimal surface. Yes, that's basically something similar what we did with the vault structure. It might require greater computing power, but would be interesting to see how the aggregated maps onto a self-folding surface. I think these are all ways to try out. Actually, I had before in the tutorial, I also had some very basic minimal surfaces in there. I think one you see in the background where it's like pulled between floors. That to be said is, of course, when you aggregate on top of these surfaces, then you lose in a way, of course, like this minimalistic approach of the surface. So it was more a playful approach to combine these two methodologies with each other, and was also a little bit experimenting what the outcome of that would be. Then Mark Foxworth. Is there a way using fields, for example, to force the aggregation to adhere more to a ground plane, but still fill a volume? I find that the aggregations are usually balanced on a single component. To answer that, yes, you can aggregate on planes as well. Also there's actually, like exactly about that topic, there's a good tutorial, also like on an architectural scale. I think it's with like little module units on Andrea Rossi's Wasp YouTube page. And like these tutorials are, I think like they're 15 minutes or something. So it's definitely worth checking them out. And I think I provided in the presentation also some links where you can find all the necessary stuff. Then the last question here, is there a way we can control the starting point of the aggregation? For example, having 2 or more points in which the aggregation can start populating the geometry. Yes, it's possible. But it's not part of these exercises. But it can be, and that's also part of like the very first answer I give. You can even put gradients and grammar rules and all of that. You can put this also into more advanced parts and then gain more control over it. I hope I could answer your questions in a good way. I hope I put them all on erledigt. And yeah, Andrea really has some really good videos, because like there's a new, the version of Wasp we're using right now is relatively new. So there's also some devlog videos with like the new functions in it, which is definitely worth checking out. And he's very active in continue the software as well, so I can only recommend that. And the next exercise is one that I would rather, it's more like a short exercise. There are only 2 new things I want to introduce to you, and some of them I talked already about. It's 2 constraints that I wanted to introduce, but also more going back or like away from this pavilion topic, which is more like a small scale intervention or architecture, and more back on a building scale or a construction kind of scale. And just because it was in the just because it was also in the reference pictures for the workshop, I wanted to integrate this definition for you guys, that you can have a look. Basically, this is just a very simple timber self-building system In the case it's distributed, in the definition itself is basically there's like a box and a cube, yeah, with different lengths, and it's just a voxel-based aggregation. There's also like another way to do it more in a discrete way, where you give like every element that's in there, kind of you define it as a Wasp object and then aggregate it as well. And to be honest, we cheated a little bit in this one, and already did like prefabricated voxels, let's say, where there are already 6 elements in it, to just go faster and achieve bigger functions. But also just what you see in this exercise, and this is why I will not go too deeply into everything. It's very similar from the population of the field aggregation of the volume, just with different components, and it should just show you in the end of the day, yeah, what's possible. And it is also with Wasp relatively easy to generate, for example, pictures like this, which is exactly the definition which is in this exercise, and with like very super simple components in the end of the day. And then of course you can, there are no limits of possibilities and of sizes that you can do, especially when you introduce certain restrictions. Yeah, for example, when you want to grow something around the building or in context, you can give in all the surrounding buildings, for example, and then you can relatively precisely tell the definition that it cannot intersect with these boundary boxes. And this is something we take a look at in this definition, or in the next exercise, which I will just open here. And just to give you an overview, I will zoom out. So what we have here, like in the upper part, is what you have just seen. So this is basically the same kind of volume-based aggregation, yeah, with the donut. Just the elements are different, but also they are kept like super simple in these voxel sizes. And in the second part, like I've put something similar to the Urban Beta, not, but the simplified, very simplified version of it. And I just want to show you with the second part as well that there is the limitations. You see the red box already looming inside of the donut, and there's also a mysterious plane here. But to that I will come in the tutorial. You know, and as I said, this one will be a quick one because it's more like a rehash of things we've done already. I want to go into the first one, and maybe I will just delete the second part of it, because this is something I think that we can do together again. I'm also hiding just some of the things right now to get a better overview. And basically, let me just go on this side here. This is the rendering you have just seen, yeah. And here you've seen that actually this is an aggregation that is completely based on 2 modules, yeah, like a cube module and a box module, but they are dissolved in a very clever way. They're dissolved in a very clever way, so you don't see kind of like this remaining voxel structure, yeah. And what you see is then rather almost something like a toy that we can stick together in different configurations, and that allows and that also, yeah, allows for interesting spaces. And how we did this is just the 2 components, yeah. So to get something nice out, is also the input doesn't have to be very complex. I think that's one of the takeaways of this one. And but for once, I also want to zoom in a little bit into the voxel And what you see inside of the voxel is what we did. These elements, they do not end with the outline of the box, which means when I copy this box, for example, so to here, when I copy this box, you can see that kind of like the elements, they align on each other and they become something like a big puzzle piece. Yeah, so basically you have always a male-female connector. When on one side something stands out of the box, it's pushed in on the other side. And like with these logics, you can build quite nice systems. Yeah, I can also let you see it again with the connections from left to right. Yeah, how they work. When they come together, they form actually one piece. And when you take one out, you can see actually how the structural integrity in this element would be guaranteed. So just for the aggregation part itself, yeah, we have here the component one. Let me check which one this is. This is the cube one. And whoops, preview off. And component two. Let's check the preview again. Yes, looks about right. Just wondering. The point is off. Let's do this again. Yeah, like, and here you see like, okay, we made like 3 connection points, also 3 connection points. You can of course do more, merge them together. In this case, also combined with a rule generator, and then aggregate it onto the field with the volume as input. Yeah, generating the field points, pulling them towards the geometry, yeah, generating the field out of it and putting it into the aggregation. So when we enable this one, we will probably not see anything because there's not a part out. So, but let me put this in. And one request is, of course, always to put the bifocals on so that you can see all the aggregations. So here we get the parts out, get part geometry, part out. So what you see, actually like super simple. And what we will do is just, we will again filter the parts by name. Use the name from before, maybe copy it already, use the other name, so 1 and 2. Then let's go here and deconstruct the part, take the transform, and here add geometry, mesh it before. And the thing is, what I created here in this box, you can see it, these elements are actually having 3 colors. And if you want to integrate the different colors of an object, yeah, or different surfaces, each one of them has to have an own transform. So basically what I will do, let's see if I group them after colors. I hope so. No, I didn't. So what we will do, then I will take this one over here. What we will do is we take this geometry, which is the blue one, give it a preview, custom preview, give it a color swatch, and which color was it? It was blue. making it a nice color. So then already having it here, then taking the whole part about the transformation, copying it, moving it up, inputting the timber part, set multiple geometries, giving it a color, of course, that fits then as well, maybe a little bit brighter here, and then copy it again. And so let's move this up, copy it again, input the red part, set multiple geometries, giving it a nice red color somewhere. So, and then of course, bringing these elements together, group them, that you don't, oops, group them, then let's see how they fit. Yeah, they're moved by 4, so I will move this with -8, and hopefully it's on top of this one. And then we'll group them again. 4, and let's see if we find how much they are moved. To move them in the box here again. I only move with numbers, yeah, so that you can always find that again. And now that we have all of this, we can copy the whole thing. Oh, no. Again, we can copy the whole right side here and connect it to this part. To get, of course, the long geometry as well. Of course, exchange here the blue geometry for the blue geometry, the wood for the wood, and the red for the red. And then, of course, we group it, and group it, and move it to was always moved by 4, move it on top of each other, -4, group it again as 1, and then no, also -4, then move it into the box again, which is 20 away. So then this should actually fit. The reset button, and something is wrong since we do not see everything here. Okay, let's check that out. Component 1 is this one, yes. So we maybe hide this geometry first of all. So we see there are either parts missing. Let's check for that. Part geometry. So let's check for the bounding boxes, and there you see, there's not all of the parts being displayed, and this is probably because we did not join the meshes. Put a mesh join in here, put this in the geometry, and we have to add a mesh join in all of them, so it's just one object that we distribute. Putting it in here as well. So, and up here as well. One more. And one more. And then you see already there's some changes happening. Let's this off again. And just to be sure, let's put the reset button, but this already looks much better. So as you can see, yeah, like sometimes like simple components are missing, and then the whole thing can look a bit strange, but usually this is easy to find. And that's just like a quick part. I wanted to show you again, like how to exchange for different surface colors. Yeah, also something relatively simple, but like also from like an architectonic aggregation, quite effective. So let's move on to the second part here, and this is where I already told you that we do here just as an aggregation, we do a grid, also very similar to what we had before. I can show you in the wireframe. This is something which is based on the beta pod model, a very simplified version. We have 3 components. One is a cube, and there are 2 squares or 2 sticks. So the knot and beam 1 and beam 2. And when we activate the aggregation, so we can quickly see, okay, we have already the donut filled with a nice grid. We can see our knots, we can see our long beams, we can see our short beams aggregated. I think what brings good variety usually in this is when you, for example, take one of the beams, like this one here, and we actually exchange it. Yeah, on one of the beams, I just basically I took the basic beam. Yeah, that would be the normal beam, and I added something like a wall element or like a flap or something like this, and it's just a simple geometry exchange in that manner. To set this geometry and -1 and put it, I think, in the right position, and then suddenly you can already just with a simple geometry change can already create something that looks way more interesting than just the standard system. What's to say here with the connectors and the bolts? When I modeled these, I always modeled distances, very small distances into them, so that you can also, when you create like a render model from them, or even only the Grasshopper view in here, that you have quite a detailed view of it in the end of the day. And usually this is all about having like the gaps modeled, and just about like these little details that make in the end the difference. And then there's one more thing, what you see here already and what is applied here already, not the whole donut is filled, and it exactly stops at this plane here. So and this has to do because there are 2 restraints that I wanted to do with you, and I first of all will delete the restraints and also reset our aggregation quickly. Now you see that actually all of the elements are distributed equally inside the donut. Yeah, it's maybe not full because there are not enough elements to completely fill it. And what I want to introduce now is like a constraint, a plane constraint, and this constraint can be very helpful. Like I said, when you have geometry you don't want to touch or you don't want to go over. So we go up here and check for the plane constraint. It's down here, and we will just integrate it, here, and you see it wants a plane, of course, and then it wants Boolean true or false if it's in a positive or negative direction, so if it's left or right of the plane, let's say. And then the third one asks also for a Boolean if it's soft or not, which means when you have a hard constraint, it means that none of the elements will go over your plane restriction. If you have a soft one, it means that the centers of your elements will not go over. So basically, there will be edges and stuff that will hang into it, but not the most part of the elements. And to create a plane, I will just simply take a point. So set one point like this one here. Oops. So like this one, no, didn't want. So now then we want to make our plane movable. So we just create a move button here with X, let's say whatever, I think it was around 18, something like this, and then we create, of course, a plane, in this case a Y and a Z plane. So now we see the plane, so this is the plane we will take as an input, and then these constraints, like you can put them into, wait, which components do they go into? Sometimes I have to look for myself. Usually we have here, this is the constraint, right? Global constraints. And as you see, when we reset the definition, you have the constraint now on. One thing, what is very important, if that the constraint works, you have to see how the like which integer is in the mode, because these aggregations have different modes, and here you see it like 0 is no constraints, 1 is local constraints, 2 is global constraints, and 3 is local plus global constraints. And this plane constraint and also the other one with the volume or the mesh that we will have, this is a global constraint that globally affects the whole geometry. So in mode, we have a set data item, and we would put this to 2, and usually it is put on 0. And here we can also still integrate the Boolean toggle, and also up here, so when you see, okay, now it's only aggregated on the other side. Let's change it back to the side, and then you can also see, since we put like a moving plane in here, we can move the plane over here, reset the aggregation, and you will see it will only aggregate until the plane. So let me group this one, and then let's put a second constraint in. We only we take the mesh constraint. Let's open Wasp again here. This is the other one. It's above the plane constraint. It functions relatively similar. So what we can do is actually we create a geometry. simply like this. Put it into Wasp. Then we can also make it movable or not. For the moment, let's just work with the block that we have. We can still move it in Rhino. We can activate these constraints. Instead of the position, which was left and right of the plane, you have an input, which means if it's true, it allows only parts to be aggregated inside the volume. If it's on false, it's outside of the volume. So we want false, that we have nothing inside of our volume, and also false with the constraint here. So I will add this constraint now and reset the definition. And as you see in this part, now suddenly, since we have a soft constraint, I think, yeah, there's only some elements working in, but not not major elements inside. And we can also, what we can also do is we can put this on true and reset it again. And then you see also there's like a much softer definition of the elements that are clustered around the mesh constraint here. And these are two constraints you can work with. What is, I think, very interesting is actually instead of using a field, you can also make your volume as a constraint. Yeah, you can activate the in button, that your aggregation only functions inside of this volume, and then you can add other volumes, for example, like windows that cut through your first window, and therefore you open up your aggregation. And since then, all of these are still movable. You have like a great freedom of adjusting everything at the later phase as well. So this was just a little introduction to voxel-based aggregations, to components, and how you can also use construction systems inside Wasp, and how you can aggregate them. And it was like a short exercise. And I would also propose we make one more break, and then we come to a larger scale aggregation, more on a tower high-rise level, more on an urban level, and we will combine that with the Enscape introduction. It will just be a basic introduction where you see the basic features of it. And it functions quite well, I think, on that scale. And I would propose we make a 5-minute break again, and then we start all over. Okay, welcome back. I saw we only got 50 minutes left. I think we can make that in a good time. Let's continue. I think I will do it like after the last breaks and just start with the open questions. In first, Mark, again, in your practice, are you using structural optimization software like Karamba to size structural members and analyze stresses on joints? If so, which software plug-in do we use? I guess let's say it like this: we don't do it ourselves. Usually, our engineers are doing it. Like FE analysis, finite elements, and all of this stuff. Like we did like a 500-page calculation for all the loads and for all the deformations, for the whole beta port system, for the stresses, for the joints, etc. They like Karamba is software developed by Bollinger Grohmann. I think they don't use it in this case, but we also worked with Bollinger together on other projects where, for example, this was used. And I hope this could give you some insights. Usually, to be honest, we as more like a architecture office and project development office, we usually outsource these tasks to the engineers. Which is also a liability in the end of the day, because we don't have the insurance to do these calculations. I hope this could answer your question, and then we can go on with the next exercise. Maybe a little intro. Exercise 5 and 6. So why 5 and 6? Because it's combined like a high-rise typology with the introduction to visualization. We will look at structure like this one, not exactly the same. These are two outcomes of the Bartlett studio. This one as well. This is a zoom in. And what we will take a look at is also something that Daniel Köhler is working on or used to work on at the Bartlett, and now also at Texas A&M with the large scale city networks. We will give like a basic introduction to geometry principles like this, which is in general relatively easy to do, and exactly with the tools that we learned in this workshop. We are now at the lower part of this graphic, and what we will look at is structures like this that are either like based on frameworks or modular or modules. I will also show you this, like once you have, it's a super simple aggregation in this case, and you can exchange it again for a lot of complexity with like a minimal effort in the end of the day. And we will take a look at grammars, especially at input grammars in this exercise as well. So we will also cover this, and we also take a quick look at how to visualize the grammars. That's also what you see here in the picture in the upper side, and the outcome we will have from this tutorial is something like this. This is here like still a bit wild, but this is exactly the same definition as this one, and in I think it's changeable in like 8 clicks or something to come from this design to this design. So also Wasp is actually a great tool to test options, to automate these things as well. And you can like already see this is only built with 2 components. And if you want to build like a proper design, of course, with proper building functions, mixing mixed use functions and stuff, you will probably not end with just 2 of the components, and they will of course be a little bit more detailed. But it should only give you a small introduction how to use the tool, and then of course afterwards it's up to you to extend your definitions on it. And I would personally be also very happy if you could share some results afterwards with us, because this I'm always very curious what the outcome will be and what other people make of it. So let's jump in. So here we go. Here you see that's actually this little tower. It now contains, I think, like 800 units or something like that, approximately. I go to shaded mode to be a bit faster again. What's very well visible is that you can create frameworks, like also like non-standard architecture, but from standardized or serialized elements, and still create like a lot of variety only with 2 elements and like a little grammar involved. And what you see here is basically similar to all the other definitions we did so far. It's only based on a box and on a smaller box again. Yeah, 2 box sizes. I think one 5 by 5 and one 10 by 5. So nothing really outstanding to then at the end achieve the goal here. But there's one thing that's kind of special about it. But now I have to switch off the aggregation that we can move a little faster in the end of the day. Because here we introduced more specific grammar rules per part. And this is something I would like to do with you. But first of all, I have to get my elements out, my detailed elements. So, -10, -10. So basically, here are like the basic geometries, you know, and this is 2 ideas for detailed geometries, but that will basically affect the look of the building very much, and the appearance in the end of the day. So what you see here is actually that we have 3 zeros in here and not only 1. Yeah, we also have 3 zeros in here. This is because there are grammar rules in there that are not related to the whole part, but only to certain IDs or phases of the part. And to do that, that we will do now, and that's why I will delete the complete left side again, because what's on the right side, this is kind of what you know already. This is what we did in the last exercise. The field we aggregate in, yeah, it's the same field than in the last exercises. Nothing has changed there, but there we have something new, how we input our parts. And basically it starts very similar, or it starts exactly similar. Yeah, we get the geometry into the definition. Let me just see, did I first use this one? Yes. Here, set 1 geometry. Then we need the points. Then we need curves. Then we need the point list. So, yeah. So okay. But we will differentiate, and we need, of course, what we need, of course, as well, we have to go into Wasp and create our connection. And now this will be a bit different than what we have done before, because what we want to do in this case is actually we want to only connect certain parts with certain parts of the other element. So there's like a 4th input here, and this is a connection type. which can be later on used with the rule generator. So what we will do is in this connection type, we will use only the top, the connections that are on the top of the geometry. So which means I think this is too much here. So we do the point that is on top, which is this one, and the direction that is on top, which is this one. Then, and we will also check the preview off, and then we will name the whole part first, and still a basic part. The whole part will be named box, let's say. Put in the geometry, put in the connection. Sorry, the panel, of course. And here we name it box. So, exactly. This time we put it a little bit away, and we use this input parameter to copy the panel. And we call the upper connection, which is a grammar now. Yeah, we input this as a grammar. We call it box top and input it, so that the definition knows this is only the connection on top of my box. And then we will make one which is called box bottom. And you might guess it, we will take the point at the bottom and we will set the curve at the bottom. And then we make a third one, which is called box side. Okay, and we will input all of the side parameters, which is 1, 2, 3, 4. No. Okay. Set multiple points. 1, 2, 3, 4. No. And we set the curves as well. Set multiple curves. 1, 2, 3, 4. And we are actually doing this to define a top and a bottom of the box, that our boxes in the future will not turn around when they aggregate. So we will define in this a grammar that says a bottom of a box can only connect to a top of a box. A bottom of a cube can only connect to a top of a cube or to a top of a box. And in the end, you will prevent that parts are on the side and connected in ways you don't want it to be connected. Then what we actually do, input here merge, and rather merge the three here, which gives us better overview of our part. So now we have the part box complete, and we do it a second time now. Do the same grammar. Let's copy the whole thing. And what we change now is actually, it's not the box top, but we call it cube top. And input geometry, input the box. Actually, we can link this to all three of them. Have less components. Otherwise, we only repeat ourselves. So make it a bit cleaner here. So we have the geometry. We set one point. We set one curve. We set one point. the lowest point, we set the direction here, and then we set all the side points, multiple points, 1, 2, 3, 4, and we set the curves, 1, 2, 3, 4. So that should do the job. We call our component cube, and of course it's cube bottom and cube side. So okay, then we have this one here, and so. And what we can do now, and you see it here already, we can, as we are used to, we maybe merge these two also together, 1 and 2, to have our parts, and our parts go into the rule generator and into the aggregation here and here. And I pre-wrote this already, because what you can do with the rule generator now, you open a panel, and also look that it's a multi-line panel, the others don't work. And then you can say box bottom connects to box top. And this is actually like here in the grammar folder. So like you defined the grammar for your elements, yeah, box top, box bottom, box side. And now in your rule generator, you can actually say, I want to connect box bottom to top, box side to box side, cube side to box side. And in this way, you really guarantee there will be no of these elements turning around, turning to the wrong side. And let's just get the part out. I see that here the names are missing, so we get the cube over here, oh, box over there, and cube in here. So get then there's the part component. And actually this we don't want to use right now. Let's put it off. Just the name filter, and let's get the part out. Yeah, the Wasp get part geometry, that we can see the outcome. And we put this one down again to say 300. Enable the aggregation. The aggregation is in the file actually. So this is over here. So here you see already how the different elements come together. You have the box elements, and you can see already that all of the box elements, yeah, they are sometimes on top of each other. Yeah, they are connected, but they are always straight. Same goes for the cube elements. And now what we can actually do, I just delete this part. What we can actually do, we can take a look at the rules that are generated with our rule generator. And to do that, let me just quickly check. No, let me undo it. Okay, sorry. Let's keep it here. We will use the rule visualizer. Yeah, so this is a relatively new component. A relatively new component in Wasp, and what we don't have provided here is the part geometries. So basically, the rule component, it wants the parts, it wants the rule as an input, then a spacing factor. We will see what that means. It wants the plane is normally set on the normal XY plane. This is text icons, and we will just take a look what this means for visualizing the parts. Parts have to be plugged in. And as you saw already, like now what you see here in the back is kind of a visual diagram of all of the connections that your rule generator made. So basically all what is in here, yeah, box bottom to box top, cube bottom to cube top is all in all combinations visualized here. And what's great about that is actually you can look at which connections you like and which connections you don't like. And then like that's what I just, you can define the spacing between it, yeah, and you can also get more or less information under each connection. But when you now, for example, say, I only like connection 27, connection 35, connection 52, then you can easily create an item. Sorry, you list basically an item in your after your rule generator, yeah, like no, and you put the connections in that you want to have. Yeah, I like connection 1, I like connection 8, I like connection 52. And what you can do with this then is provide your rules into the aggregation and restart it, and then basically you will have your aggregation only with these rules provided. Yeah, so these rules are right now quite limiting because I only took like 5 of them out or something, so it's the result will be of course always less limiting and never completely filling the base plane that's in there. But this is a nice way also to have more control over things, not only with the grammar, but also with really actively going into the rule set and also visualizing the rule set. And now let me just refresh here to what we had before exactly. Then I will put this preview off. And what I will do here is, again, I have these units. Here, I think I already inputted them in the transform. And I have to put the units, of course, again in my original position and enable the part deconstruct, yeah, to get the transform out. And what you will see, of course, now is that the complex elements of my skyscraper, of my high-rise, are in there. Yeah, now with 200 elements, I can also make 800 elements, maybe to make it a bit more interesting. So now we have 800, yeah, and then we generate something, yeah, like a modular skyscraper with a frame network with pods inside. That is, I think, already quite interesting. Yeah, I put the volume so that it grows a little bit over the others here as well. And what you can, of course, then easily do is exchange the geometry inside of the model. And when I exchanged the geometry beforehand already, and I baked it just to be a little bit faster. So basically, this is the same aggregation, but with the other components, but it's still the same box and the same box and the same cube. now it's an overlay between the two because this is because of the previous. Let's go into shaded mode. And I think you will not see them for now. So actually, we have kind of the same tower aggregation, but like a different, completely different look and feel. And what I will do now, I will also bake. Oh, no. So I will do bake geometry 2. Then I will copy this layer structure. So duplicate layer. I will put them into my new bake geometry. So, and I will delete. Oops. So these are too much here. Oops. Let's delete them. So then we have the block bag and the cube bag, and let's put this here in here. Exactly. So we go back to Grasshopper and put them visible. So, and then we'll bake some of these geometries. So this is the wood frame for. This is the wood frame for the cube, not for the box. Okay, so we bake it. Bake geometry 2 with the box. Let's put it in geometry. I think the layer names need a little bit different. Frame class, unit, and circulation. Let's call it here as well. Frame. Unit. Maybe then the unit is not in green, but let's say gray. So for the layer color, and here the unit is wood tone, something like this. So then we have this. This is the circulation of the box. Then we bake it on the block circulation layer. This is the glazing of the block. We put it on the glass layer of the block. Geometry 2. Put it right now. And we put here, this is the pots. And the pots we put here in the unit. Now we do the same thing again. This is the frame. Put the frame in the cube frame. Always group it. This is the circulation. We put it in the circulation. We group it as this is the glass, of course. Put it in glass. And this is the pot unit, and we put it in unit. So take it and we switch that off again. Switch on the layers, visibility. So, and then you see, like, I think the tower is completely in Rhino now. Yeah, looks like it. Then I can switch like disable the aggregation here, and we minimize this. And basically, that was like all the Wasp tutorials for today. And I think I would like to use the last 20 minutes just to give you an overview on how we can visualize what we see in front of us. Maybe just quickly sharing my screen again. These are just quick shots from Enscape. Just as a little introduction for the visualization, I put also some links in this presentation. Yeah, like you can get good 3D models for background objects, for everything. Yeah, staffage objects from Quixel, from Sketchup, from Warehouse. In these tutorials, we kind of use them already a bit. Personally, I have two favorite texture sites I always use. One is called Ambient CG and one is called Polyheaven. You can download free 2K, 4K textures with all roughness, normal maps, everything you need. They are really good to implement it. Then what we will take for visualization in this tutorial is Enscape. So if you installed Enscape, please go to options and then into toolbars, and then you will see there will be an Enscape layer, and then please activate the Enscape toolbar. This is these pictures are a little from an older version, but the Enscape toolbar will look like this. I always put it here on the side. This is how it looks, and basically this starts the real-time render engine. This one enables and disables the live updates. So basically, when you change something in Rhino, it automatically changes in your real-time render engine. This synchronizes your camera position. This means when this is on true, that Enscape automatically will always go with your Rhino camera. So when I move like this, it will also move the camera like this in the Enscape rendering. And this is the object library. I will go into this quickly right afterwards. Here we can import materials, we can tune and make own Enscape materials, which is very valuable and very good. I use usually the 2K textures in high resolution. That I made a little library downloaded also from the websites I just showed you. And yeah, and that's just as a basic intro. What you see down here is already from the asset library. These are the trees. I will just open it. Enscape, this asset library only functions when you're in the internet because it downloads the models directly from there. And when you open this, you will see there's like a vast overview of elements. Yeah, like here you have your menu, you have animals. Yeah, you can place wild animals. Yeah, a lot of butterflies, like cute dogs. You have a lot of people you can place. You have a lot of vegetation, and I would just quickly go into the vegetation one. You can select a tree, just click it, then click a surface where you want to place the tree, and the tree gets placed here. Yeah? And then you can, of course, adopt it. What I did already here, I placed like a lot of trees already. Maybe I would go to street props, since we have some streets here. Yeah, like you can place like a crosswalk. Yeah, you don't even have to model all of these little things here anymore because they are all already included. Yeah, from little signs to street lights. Yeah, everything that makes your scene more realistic. Yeah, you can just distribute them. I'm just doing this like very quickly right now. Yeah, like you can put some benches here in the park. Yeah, and everything of this makes it will make it like a quite realistic, like your picture. And usually it takes like half an hour, yeah, to prepare a scene properly, that you can render it properly. I will put maybe some vehicles still in there and some people, yeah, just to cover like the basic things. You see already there's like a lot to load. Yeah, there's also here a Tesla truck. There, I think in the new version also has some electric cars, which I personally would prefer in renderings. It's easy to place. Basically, what you place, there is proxies. Here's like a Tesla. And they're like relatively easy to handle. You can just also take them, copy them. Usually, like I have scenes with like thousands of trees, yeah, and the software is really fast, and usually you can place a lot of objects into your scenes without it crashing. And let me get back to the asset library. Yeah, let's place some people in there as well. I will do this more randomly now, just to be a little faster. So here you can also see this. It's like all kinds of people. Same thing. You click it, and then a person gets placed. Yeah, you click the surface, you click the person, gets placed. And it's really just like almost a drag and drop scenario. Yeah, we can go on our structure. This is like all meshes now, like they always want surfaces. So it would take a little longer to place this, but just on the ground level, I think that's already quite good what we can do here. And I will just take these people, can take in the end, and then you can just group them and move them around, copy them in all areas, that it's looking lively and maybe a bit busy. That's actually what you have from such a streetscape, I would say. Other side. So I really do this like really fast and also a bit randomly now. Of course, when you take your time to create these scenes, this is of course very valuable, and also very fast results you get out of it. And for now, this is enough for me. But now what I want to do, I want to see my scene already. I want to see what it looks like. So let's start the render engine. It's also the first time you will start it. It will always take a bit longer because there's a lot to process in the scene. Of course, there are a lot of objects right now. Yeah, I hope we don't have to wait too long till it starts. So that's the introduction screen. What's good about Enscape, it's like it's for students for free for I think 48 months for sure, or 24 months. What's great about it, it's not only in Rhino, but it's topping up on SketchUp, on Revit, on Archicad. I think there's a lot of lots of programs. It's just plugging in, and it's in this case for Rhino, it works in real time with Rhino. If you move an object in Rhino, it will automatically also move in Enscape, so you can actually test a lot of options in there. It's quality-wise maybe not as real and crisp as like Keyshot, but it's more catered to the architecture market. So you have like a lot of skies, like the right proportions of the backgrounds and all of that already pre-prepared. And of course, everything is in real time, which makes it a big advantage actually in my point of view. So let's see. So it's hopefully the last seconds of waiting. Okay. Yeah, sometimes it takes a little longer, I guess. Let's see. And there we go. And like this is already like the base setup, yeah. And I will just quickly show you, yeah, some quick checks what you can do. They have like Enscape, like a good website, very good tutorial videos online. It's very easy software to learn. I think it also made quite like a change in all of the architecture offices at the moment, and also has quite an impact on render firms at the moment. So basically, what you see on the right side is a panel with all the inputs you can give. Yeah, so you move like in a computer game with the WASD input. Yeah, with E and Q you can go up and down, and when you press Control or Shift and Shift, when you press both, you move very fast. When you press only one, then you move faster, and then you move fast when you press both of them. And here you see already, yeah, it's our speed scale. For example, when you press the space bar, then we will actually, like, there's a physics engine deployed to your movement. That means like there's an object detection. You will not be able to walk through objects again. So basically, you will automatically stop at the wall, basically exactly like in a computer game. And that here just for the first steps of the view. What we can do now is this is probably the most important button, the visual settings. I will just give you an introduction here quickly. So, what you can do here is, for example, you can give your buildings outlines or take the outlines away. It depends like how diagrammatic your visualization should be. Are you doing a diagram or not? Then you have exposure. You can change it, of course, to make it brighter, less brighter. You have a field of view for your camera. It's quite basic. So let's keep it like this. You can, of course, go from a perspective to a two-point perspective. You can go to an orthographic perspective if you want diagrams. Very helpful. You can put the render quality down if your computer is not as good. It will run faster. Then when we go to image, what we have here, we have color temperature, we have saturation, vignetting, motion blur. It's all things you can change in there. Then to make, I think very good is actually the fog option. You don't see it right now because you have white background. When you're in sky, you can take the white background off. And then we will get a real sky background. And here, of course, you can change the density and variety of the clouds, the cirrus amount, the contrast. You can, in the atmosphere, brighten up the sun. Yeah, it gets very bright, very low, and you can also give it like a fog intensity, the height as well. Of course, when you have a big sun, it will shine through the mist. There's volumetric lighting as well. Integrated already. Then what you will see is also when you press the U button and the I button, you change the time of day. I will just quickly do that. So you see that the sun is going over, and then you can also change the position of the sun when you press Control and U and I, then actually the sun moves around the scene, yeah, and you can actually change like lots of things. Here you see lighting. So maybe I will just go. I haven't textured it yet, but it still looks already okay, I would say. And then put materials in, like of course, when you put like more realistic glazing as a material, or realistic glass, and of course it will immediately look much better and very fast as well. But just for giving you the basic introduction for this one, I think that's enough. We can maybe play a little bit and reduce the fog. Here again, let's see, atmosphere, fog intensity. See about this. Go a little, stand also the other side here, for example. And then, of course, we didn't place people textures inside of the building over there. It's just like a basic introduction that you get an overview what's possible with the program. And of course, you can always change the time of day. When you have placed lighting in your scenes, then they will automatically, or you have lights in your scene, they will automatically switch on at night. I don't have any in my scenes, so it also stays dark, of course. And then we can also optimize, yeah, these like nice light effects coming through the building. What I usually do is I create renderings, so at least 4 or 5 different renderings with different moods and different lightings, but from the same perspective, and then overlay them in Photoshop at the end, just to have like just to have more variety and create like more interesting areas with shadows in one place, and then sometimes in other places as well. And usually this works quite well, and you can, as you see, you get immediately good result. When you wanna, you can make a shortcut to save all of your pictures, like here in the output section. Yeah, you can define the resolution. Mine is now on Ultra HD. You can define if you want to export channels, like the ID channel, def channel, the format, of course. You can make videos also very fast. There's a whole on video panel in it. Basically, you make keyframes. You set the keyframes, and then the camera extrapolates automatically. So this is yeah, quite comfortable to do, actually. And I will just place on my shortcut that it makes one rendering. Probably it will take a while, since the geometry seems yeah, quite complex. And let's see if something happens. No. Not moved. Okay. Okay, so let's see. Okay. Ah, yeah. I have a shortcut like Shift Plus to make a rendering. It will automatically open the picture folder on your computer, and automatically also that you have no double saves. It will save with the year, with the months, with the date, and with the time actually. So like every rendering has a unique code, and you just press save in the end of the day, and then it will render out the image in the quality you want to you input it. In this case mine was Ultra HD, which takes a little bit longer, but usually like a rendering takes between like I would say 2 seconds and 2 minutes or something like this. So it's super fast. Here you see it already exporting the image, and it's just a matter of seconds. So, and now we can actually open our picture folder. As you see, so this was around, I don't know, 10 seconds maybe. And here I did also some this week already. Here you see kind of that there's our final image. Of course, when you have more time, you can always tweak this more and more, make it nicer, place more people, vegetation to make it more realistic. But this is already the image. This is one I did from the other aggregation before. You can see there are more outlines in this one. It's a bit more graphical style, a bit brighter. And this is like how you have in the end like a lot of variation. And this also brings us to the end actually of the webinar. I'll take a quick look at the Q&A, I would say. And let's see what's happening in here. Thanks for your very productive webinar. Could we get in touch via email? Of course, just write me. That's always an open door. Is there a place I can find an explanation or the script of the EU Bauhaus project? Yes, there is, but it's on my computer.
I'm sure it's. Is it on your website? I mean, not the script, but I mean information about the project. So
the information, is it? I'm not sure yet. Actually, I'm not sure if it's super updated. Not 100% sure. If not, it will come this year at some point.
Well, really good, clear webinar. I mean, seems everyone was able to keep up or at least pay attention. Not too many questions or difficulties. I think the setup of the files was really good, and everything seemed super nicely explained. It was really, really fun to watch on my end, at least.
Yeah, cool.
Really
I'm very tired already.
But it goes pretty quickly, I think.
It really is. You said so. It really did. I was really afraid before, but it's like really could do another hour.
Don't tell them that. Does anyone want to ask any more questions, or if anyone wants to come on the camera and ask anything, we can put your camera on. Just click the raise hands button if you would like to do that. Sometimes people want to do that, sometimes they don't. Well, it seems I don't know, it seems everyone's pretty good.
Then I'm happy.
Yeah, I mean that's good, right?
I
I
hope
think
so.
everyone was able. I think the files like that you made were really, really big for them. So
Yeah, it's also, I have to say, like also some of the, like they also, I have a very strong computer, so I hope they are also, all of the files are working on the other computers.
are you working on a laptop now or a strong?
Yeah,
strong
no, it's, I have one of these Razer
Oh, yeah.
laptops.
Gotcha. Yeah. Walter is asking if you have any other projects that will be built.
That we will be built.
Yeah.
No, right now it's all beta port. I think that will be the rest of the year actually. Like it's our
Ambitious project. So
ambitious project.
yeah.
Sleepless nights.
Yeah. Cool. Well, yeah. I mean, if that's it, we can end this thing and let you get to your sleeping night.
Yeah, like thanks for having me. Yeah,
It was really good.
it was a pleasure. I was
Thank you.
a bit nervous before, but I hope everybody learned something and it was a good pace and everything. And would be cool to get some feedback from the students who were here, or if anybody make some projects out of it, just send it to us. We're always super interested to see the results and what you make of it.
Yeah, and yeah, just as a reminder that everyone's still here. Yeah, just check the email we sent before the webinar. It has information about recording and all that. Yeah, those will come. Sounds good. Cool. Let's end it. See you, Marvin.
See you guys. Thank you
Yeah.
so much.
Bye.
Tschüss.